Jamal, Respected Assistant Secretary Dr. Abdul Samad, the Vibrant Principal Dr. Ismail Mahidi, the Honorary Member Director Dr. Nihal, the Vice Principal Dr. Mohamed Ibrahim, and other management committee members, faculty members of various departments and students. I welcome you all. I wholeheartedly thank Dr. Mohamed Hussain, Principal, College of Science, Engineering and Management, London, the United Kingdom. He is the chief guest of today's ICC International Conference in Innovation International Conference, 7th International Conference of today. I have contacted him only through email. He readily accepted the invitation. He is a very famous scientist, one of the pioneering scientists in the field of corrosion. Without any hesitation, he immediately accepted the invitation. There's a lot of work, lot of engagement, but has accepted. It is his politeness. So, such a personality of such a caliber is today with us in the Zoom meeting for the inaugural function of our international conference. So, on behalf of the McDonald's management, the staff members of our department, and the students of our department, I wholeheartedly welcome Dr. Mohamed Hussain, the Principal of Science, Engineering and Management College, London. Today I talked with him on phone for a couple of minutes. I requested him, sir, it's not a final, it's not an end. We'll often disturb you. So we'll have a collaboration with you. Immediately he said, with pleasure. Okay, we'll do. That is the capacity and caliber of such a great personality. Once again, I thank him on behalf of the Department of Chemistry as well as the students and the organizers of this conference for accepting our invitation. Then I welcome the organizing secretaries of this conference, Dr. Beriyasamy, Dr. Masood Ahmed, and Dr. Shamshad Beham. It's not a one-day show. A lot of spare work is there behind the conference. For months together, these three people, not only these three people, all have worked, but under the guidance of these three people. So, on behalf of the staff and students, I wholeheartedly thank and welcome the organizing secretaries, Dr. S.K. Beriyasamy, Dr. Masood, and Dr. Shamshad. I welcome a teacher, Dr. A. Mohamed Qasim, silent in his sitting. I welcome Dr. Sina Mubarak, the senior faculty of the department, Dr. Jafar Ahmed, one of the senior faculties of our department, as well as the coordinator of hotel management, Department of Hotel Management. He is expert in organizing the international conferences. I welcome Dr. Zakir Hussain. He witnessing and smiling. I welcome Dr. Jamal Abdul Nazar, another senior faculty member. He is good for me in PhD. He is the senior of my PhD and he has guided a lot, he has helped a lot for my PhD work. So I submit my sincere thanks to him in this podium, as well as I welcome great gentlemen. I welcome Dr. Riyaz Ahmed and other faculty members for my own students, just like my sons, Dr. Yasin, Dr. Abu Tahir, Dr. Rafi, Dr. Logan Adam, Dr. M.P. Purushothaman, Dr. Anwar Sadiq, and above all, Dr. Sayyidi Balusha, the coordinator of the hostels. Silently is helping me and also helping the department a lot. I welcome the other faculty members, the teams in the MC desk, princess not being here, in the MC desk, and my very dear students. Once again, I welcome. And I pray Almighty for the very good conduct of this seminar. I thank the organizers of this function to give me an opportunity to welcome the gathering. Thank you very much.
Thank you, sir, for your kind words. Chemistry, the central science of both king and queen, because it provides a foundation for understanding both basic and applied scientific disciplines at a fundamental and advanced level. The moment has came, and this is the time for us to break through the conference. Here comes the nice gentleman. Leading behind the successful program is our beloved Dr. S.K. Periyaswamy, Organizing Secretary and Convener, ICICER 2022, to spell out the theme of the conference.
Good afternoon, Honorable Secretary and Correspondent, esteemed President, respected Assistant Secretary and Floor Principal, respected Vice Principal, Additional Vice Principal, HOD of Chemistry, Academic Directors, Distinguished Resource Person, Dr. Mohamed Dr. C. Marshall Anandan, Dr. M. V. Anil Kumar, Professor Dr. K. N. Sirajuddin, delegates, delegates, faculty members, guests, and young and energetic research scholars, students, ladies and gentlemen. A very good morning, all gathered here. It gives me great joy and pleasure to emphasize the theme of 7th International Conference on Innovations in Chemical and Environmental Research, ICIC, year 2022. The chemical research finds that environmental information disclosure has a positive effect on economic performance. The environmental research applies innovation to design and realization of chemical product and process that have a smaller environmental impact with regard to waste produced in both manufacture and use. It is one of the key areas of chemistry where the drive for novel research solution in academia is equal by industry. The primary goal of event is to culminate erudite scientists to exchange ideas at the cutting edge discipline of multidisciplinary nature. Recent significant discoveries will be deliberated by internationally acclaimed scientists, which will throw light on their achievement in the discovery of chemical and environmental process and their industrial applications. The conference provides a platform for the researchers from various parts of the world to take up this issue and that novel ideas, research findings, and bring a great breakthrough in doing eco-friendly research. The aim of our conference is also to connect intellectual people from reputed institutions across the globe with budding chemists. The conference covers the thrust areas: organic synthesis, phytochemistry, computational chemistry, crystal engineering, organometallic chemistry, bioinorganic chemistry, environmental chemistry, bio-nanotechnology, green chemistry, and material chemistry. In this aspect, we have chosen the speakers to share their expertise with us. The overseas speaker is Dr. Mohamed from the Principal College of Science and Engineering and Management, London, UK. Sir will inaugurate the conference and deliver keynote address on forming a one-step method for making 1D, 2D, and 3D bulk nanostructure materials. Dr. Srinivasa Anandan from Achi, Hyderabad. Sir is our illustrious alumnus. Now he is holding a position as senior scientist in Center for Nanomaterial, International Advanced Research Center for Powder Metallurgy and New Materials, Hyderabad, Telangana. Sir will deliver an invited lecture on design, development, and demonstration of advanced nanostructural material for energy storage applications. Dr. N. V. Anil Kumar, Associate Professor, Senior Scale, Department of Chemistry, Manipal Academy Higher Education, Manipal. Sir will deliver an invited lecture on designer molecules for pollutant removal in situ studies. Next one, Dr. K. S. Sirajuddin, Head, Department of Basic Medical Sciences, International Islamic University, Malaysia. Sir is also one of the other illustrious alumnus. Sir will deliver an keynote lecture on natural product and neurodegeneration and to follow address of the valediction. So we are fortunate to have these eminent scientists for their auspicious occasion. We hope that you will be enlightened. An amazing response has been shown by the participants. We have received more than 123 abstracts and 116 registration for the conference. On behalf of the organizers, we acknowledge all the faculty members, paper presenters, and all participants from Punjab, Madhya Pradesh, Maharashtra, Odisha, Karnataka, Uttar Pradesh, Bangladesh, UK, Malaysia for starting their research inventions in this international platform as abstract. At this juncture, I would like to express my deep sense gratitude to our secretary and correspondent and treasurer, assistant secretary, directors, principal, head of the department, and our faculty members for their fullest cooperation and support for the conference. We assure that this conference will enable the participants to find new area in their research field. It will open up the link for future collaboration across the world. We include value for participants and support for the conference. Thank you. Have a nice day.
Thank you, sir. Here's a big and warm hearty welcome to the kind-hearted man with sound knowledge in chemistry, a fascinating teacher and a good disciplinary aide. Dr. As a remembrance of this event, the department has come out with a souvenir containing research articles that are to be presented. We request our head of the Department of Chemistry, Dr. Mohamed, sir, to release the souvenir. I kindly request Dr. M.C. and Dr. Mohamed Qasim, sir, to receive the first copy of souvenir. And I also request all the professors to kindly join with it.
No, முன்னாடி பேருங்க. பாய் முன்னாடி பேருங்க பாய். சும்மா வயர் முன்னாடி போங்க அவ்வளவுதான்.
Thank you, sirs and dear professors, for making this moment pleasant and lovely. Here's a big and warm hearty welcome to the kind-hearted man with sound knowledge in chemistry, a fascinating teacher and a good disciplinary aide, Dr. A. Jafar Ahmed, sir, Associate Professor of Chemistry, to introduce the chief guest. I request all the dignitaries who are on the stage to please come down.
Bismillahirrahmanirrahim. A very pleasant good morning. All gathered here to witness this 7th International Conference on Innovations in Chemical and Environmental Research, organized by the PG and Research Department of Chemistry, Jamal College. Indeed, it's a very great honor to me to stand before you to introduce the chief guest of today's inaugural function of this conference, Dr. M.S. Hussain. Our chief guest, Dr. M.S. Hussain, is an academic and a specialist materials engineer with special interest in surface engineering, material selection, failure analysis, corrosion inspection and monitoring, nanomaterial synthesis and nanomechanical testing. He completed his BSc in material engineering in Wolverhampton University, UK, MSc in University of Manchester, and PhD in material engineering in Aston University, Netherlands. He started his career in 1995 as visiting professor in Wolverhampton University. In 2001, a visiting scholar in University of Cambridge. In 2004, as a senior lecturer in Dubai Industrial College, Saudi Arabia. Then from 2006 to 9, as a senior scientific officer, a coveted position in government of Saudi Arabia and many coveted positions in industry, different institutions. From 2019, he is the principal of College of Science, Engineering and Management in London. His area of specialization in is corrosion prevention, synthesis of nanostructured materials for high temperature corrosion applications. He is a pioneer in the invention of the process of synthesis of nanostructured nickel for high-speed electric deposition and direct plating on aluminium, titanium, and stainless steel without any pre-treatment. It is a very applauding work which has carried out. He is a guest editor of Journal of Experimental Nanoscience, editorial board member of Journal of Computational Material Science and Surface Engineering. He has been a resource person in many conferences throughout the globe. Has got more than 100 publications in the field of nanochemistry and other fields, including patents, books, book chapters, referred papers, etc. He has successfully supervised more than 2,000 vocational candidates and 30 PhD and ME candidates. He is a management consultant, a researcher on par, a very good human, the befitting person to inaugurate this 7th International Conference on Innovations in Chemical and Environmental Research, ICICER 2022. So, we are very fortunate enough to have you with us to formally inaugurate this conference. It's such an eminent person with us to address the gathering. On behalf of the College Management Committee members, principal, my head of the department, my own colleagues and students, and all the participants from all over India, I accord a very cordial and warm welcome once again to you. And I take this opportunity to thank Dr. M.S. Hussain for having accepted our invitation to formally inaugurate and deliver the keynote address on high-speed electro forming, a one-step method for making 1D, 2D, 3D bulk nanostructured materials. Sir, the podium is open for you. I wholeheartedly welcome you, sir, for formally inaugurating this function and also to deliver the keynote address. Thanks for the opportunity.
Good morning. Can you hear me? Can you hear me?
Yes, sir. We hear your voice, well.
Could I share my screen, please? Could you allow share screen, please?
Yes, sir. We have you, sir. You can share your screen, sir.
I can't see my screen. Okay. Okay. Can you see my screen?
Yes, sir. We are able to see your screen, sir.
Okay. Good morning, and Mr. Chairperson, the Principalship of the College, and the Conference Organizing Committee. I would like to thank you for having me today. I'm really very interested to know more about the college and whatever you do. So it's quite late here. It's only about 5:45 in England. So I didn't sleep last night. I was waiting for this and I'm really tired now. So hopefully it's a very nice thing to have conferences that enables people to get together, exchange knowledge, and that becomes a very important thing, especially for the young researchers, people doing masters and PhD programs. So I hope, inshallah, we will be able to continue our relationship as a researcher in the future as well. I have been working on many things in the past, and maybe I could start with some sample. Can you see this? This is a steel product, something we use for in curries and things, and it is rusted. There's an oxidation layer on it. And then we have aluminium. This is also used in the household, and we can't see anything. There is no rust on it until we get some white rusting on it. And then we have stainless steel. Can you see it? This is like a, yeah. Now all these metals, stainless steel, aluminium, and steel as a whole, they have oxide layers formed on the surface. So one of the things what I'm going to talk about is the template-less growth method for depositing nickel, cobalt, nanorods, nanowires, nanocrystalline films on aluminium, titanium, and stainless steel. All these metals, aluminium has got an oxide layer, which makes it protective, but the oxide layer is not very strong. Let me see if I can. I can't move my slide. Okay. So I'm talking about a normal.
Okay.
Say, for example, if you look here, this is a very basic electroplating process. We have got an anode, we've got a cathode, and most of you are chemists, and you know the basic chemistry of that. So the solution acts as an electrolyte. So the copper, for example, is the anode. It dissolves and it is deposited on the surface of copper. And this is what we call electroplating. This is the history of electroplating, which started a few hundred years ago. And as I'll very quickly touch upon the history, and it started like 1772, Beccaria successfully deposited metal by discharging something there. And Galvani discovered the physiological effects of electricity. And in 1796, Volta demonstrated the pile. So there has been some changes historically a few hundred years ago. The art of electroplating was invented in Italy, and then in Britain and Russia independently devised a metal deposition in the 1800s. And according to Birmingham Jewelry Quarter, that's where I am. I live in Birmingham, which is the second largest city of United Kingdom. And Jewelry Quarter is only about a few miles from where I am. And as an interesting information, if I don't know if you know who actually started the electroplating as a process as we know. It is a Dr. John Wright. He was a physician, an orthopedic surgeon, and he was interested in electrodeposition. So he used to come in Jewelry Quarter and do some work. And he actually started the process. So after his he got this process patented, And then there are two brothers, Richard Alkington in Birmingham, and Henry, the two brothers took his process and started the new patenting and new business in Birmingham. And then in 1857, the new wonder in the economic jewelry arrived, which is called electroplating. The process first applied to costume jewelry. And then in 1927, I'm giving you a bit of historical background. There's sodium zincate, which started as the immersion, because it's very difficult to plate on aluminium. No one has done it. So in 2006, between 2015, I have invented a process called high-speed electroplating, which I've used to plate nickel on aluminium, titanium, stainless steel without any. Hello? Can you hear me? Hello?
Yes, sir.
Okay.
Yes, sir.
Okay, you have to, sometimes I don't know what's happening. So what it is, this process, as you know, nanocrystallinity is an important issue in engineering and in chemistry. And we have different processes of making or producing nanomaterials. So in this process, what I've got, I'll show you in a second, high-speed electrolyte movement, and how we can plate nickel onto aluminium, titanium, stainless steel without any pre-treatment. So what is pre-treatment? For example, we do electroforming. I don't know if I have to explain what electroforming is. Electroforming is like a 3D forming of materials by electroplating. So we have a component which we want to manufacture. We do the design, make the cathode of that, and then deposit on that metal. And then we get different kinds of, these are the different things which has been electroformed. And these are very important issue in the manufacturing of materials. So what happens is these electrodeposits glow in a columnar manner, metals nucleate. So as you know that when you start electrodeposition, the metal goes from the electrolyte onto the surface of the metal as small particles. Losing some of. So why, in terms of aluminium is the second largest commodity or metal which is used in the world. It's cheapest after ferrous metals and the second cheapest of all commercial metals we use. And because aluminium can be machined easily, it's cheap, properties are good. So we have a lot of important things with aluminium that can be used. So the aluminium is an important material for us in the surface industry and also in manufacturing industry. The surface of the, as you know, that aluminium corrodes in the sense that we get oxides on the surface. I've got a battery problem. Okay. So if you can see that we have some of these things in the home I've shown you. The problem is we can improve the quality of aluminium by anodizing or by plating or coating nickel on top of this material. Anodized coatings are excellent for many purposes, but oxide layer is brittle and forms insulating layer on the surface of the material. So we have a problem. So I have shown you here, electroplating is an industrial analytical process which can be coated on one metal to another, whereas anodizing is an electrochemical process in which the electrolyte passivation occurs and deposition of a metal oxide of the different metal on the surface. So electroplating is depositing metal on the surface of a metal. And in terms of the anodizing, we are thickening the oxide layer which is present on aluminium. So it is the oxidation of the surface, increasing the thickness of the oxide, but that oxide is non-metallic. So the biggest problem we have in electrodeposition is, this is another example. In India, you must have lots of anodized aluminium, like teacups, plates, and other things which has got different colors. We anodize and then color it. So I'm giving you some samples of aluminium anodized samples. But in my case, because aluminium has got an oxide layer, which is non-conductive, and if it is non-conductive, can we deposit nickel on it? No. So the surface, what we do, we have to take the oxide layer off from the surface. We have to remove the oxide layer. It's a difficult thing. And once the oxide layer is removed, immediately we have to deposit another layer of metal, which is zinc. So we put a layer of zinc, and zinc becomes attracted to nickel. So we can deposit nickel on aluminium after removing the oxide layer. So we call it zinced layer. The function of this immersion coating is the replacement of the natural oxide layer present on aluminium, irrespective of the process. And the success of any immersion process depends essentially upon the thin, uniform, adherent initial film which is deposited onto the surface. Let's go a bit. Now, since when I started my research and when I did deposit nickel onto aluminum surface, and I had some problems because when I wanted to patent, as you know, when you want to do some patenting, you have to apply to the patent office. I was in Malaysia, and they said, look, there is a patent, US patent. A method to plate nickel onto aluminium is described, produces thin coating of nickel on the surface of the aluminium. And so how can you do something new? There's another patent. I'm going through the patent selection process. This patent number 440414415, this process involves steps of electrolytic or electroplating coating layer of nickel by immersing the substrate in a hydroxide solution. Now, what I'm talking about is my process is electrodepositing nickel on aluminium without any other processes, without removing the oxide layer, and then without putting a layer of zinc, and my nickel will be on the surface of aluminium directly. That's my process, which is I mentioned at the beginning. Now, as I go along, I get all these processes which have been patented in the USA many, many years ago. And they're saying they can deposit nickel directly. But if the metal is uniform, the problem is if the metal is uniform and it is homogeneous, then we can deposit nickel quite easily by removing the oxide layer. But you know, as you know, aluminium has got thousands of grades, and we put different metals and elements in aluminium to make it hard, make it soft, make it more flexible. So to increase the properties of aluminium, we use different elements. And as we increase the alloying element in aluminium, it becomes impossible to deposit nickel. And there are many reasons why you want to deposit nickel on aluminium. So sodium zincate was the one which was done in 1927. And if I work for a company called W. Canning, based in Birmingham, and they're still making those solutions even now, which is a process of removing the oxide layer and then putting a layer of thin layer of zinc. So the prior arts disclosed different methods to deposit nickel onto aluminium. However, there is no simple method that would enable nickel to be plated directly onto the aluminium oxide layer. So this is my the first invention which I made in 2007-8 when I was in Saudi Arabia. I can't really show you much here. I don't have this machine anymore, but I have improved. So basically, I just wanted to show the historical beginning, the first high-speed turbulent flow electroplating. I'll talk it through. There's more interesting things coming up. So basically, I'll come to, this is an electroplating process where, as I showed earlier on, nickel is deposited from a anode to a process here. So there is an electrolyte. So you dip the metal, whatever your anode is, and you dip the metal, which is the cathode. So you pass electricity, and then metal goes from the solution, deposits here, and you get a coating of nickel, or it could be copper, or it could be zinc, whatever it is. So there is no pressure for the solution. The only thing we do agitate the solution with a lot of pumps air. But in this, I'm having a little bit of problem in showing my, if you look at this, can you see this? This is my nickel solution as opposed to the nickel solution here. And then I pump the nickel solution from here, it goes up. And then here, I have the difference between this anode and cathode is it is in an enclosed environment. The solution is pumped at a very high speed between the anode and the cathode. So I'm pumping the solution at about maybe 3 to 5 meters per second. And the solution, if you look here, I've got the nickel solution, I've got a pump, I'm pumping the solution, and the solution is between the anode and the cathode. The cathode is a thing which will be coated with nickel. And you can see that I'm showing the arrow is going back to the solution, and it is moving at a very high speed. The solution is moving at a very high speed. So that is my innovation, that it's not just agitation and pumping. The pumping of the solution is. So what basically I have said, we have the surface of aluminium, and aluminium has got natural oxide on it. So schematically, this is what I've shown here. And the oxide layer is non-conductive. So if I want to plate nickel onto aluminium, this is non-conductor. The solution would not deposit here because this is a non-conductive solution. Amazing thing is I have managed to deposit nickel on aluminium surface, which is called non-conductive. So for many years, I didn't know what has happened. So this is, the red thing is the deposition of nickel onto aluminium. So the layers of nickel is forming, and then we have got a good deposition of aluminium is here, and a good deposition of nickel. So nickel has been deposited on a surface of aluminium, which is non-conductive. If you speak to anyone, if there are any specialists amongst you in electroplating, you'll say that you cannot deposit nickel directly onto the surface of aluminium because it is non-conductor. But this is what I've done. I'll show you samples here. This is a lid of a pot. It has been plated with nickel. The full surface I've plated with nickel. Aluminium is plated with nickel. And I've got smaller samples. And this is a piece of aluminium, also plated with nickel. You can see nickel and chromium. So I've finished with finishing is blue finish, which is a nickel chromium. There are plenty of materials, aluminium, which have been plated with nickel. Now, most of the people will say that you can't really deposit nickel. Now, if you look at this cross section here, this is aluminium substrate, and this is your nickel, deposited nickel. And at the interface, you can see there is no crack, no breakdown, nothing. There is adhesion is excellent. Can you all see? There is no break, nothing here. So good adhesion there and thick coating there. So proof that, and then my hypothesis was that as I pump solution from A to B, between, as I showed you, there's a narrow gap between the anode and the cathode. So I'm pumping the solution at a very high speed between the anode and the cathode, and I have got a high voltage. As you understand, as you can think, when you have got a narrow gap and you're pumping high voltage, that creates a lot of pressure on the electrons' movements. So basically, I'm saying that because of the gap, narrow gap, high speed movement, and then you have got the anode and cathode electrical, like a pumping between that. So there is my non-conductive surface of aluminium. So something is happening here. I'll tell you a story as I go along. So if you try to remember that I've got my anode and the cathode, and I've got a pumping solution at a high speed, what does it do to the surface? As I showed you earlier on, the oxide layer was non-porous. The aluminium could not be seen without at any way. The aluminium could not be exposed. So what it is, I've got a turbulent flow, and some of you might understand the turbulent flow, and there is a laminar flow. The turbulent flow means that there is a good mixing of the solution, and sometimes these two sections could be very stagnant. There could be no flow at zero flow here, at zero velocity. Okay. Now this is one thing of what I'm trying to do is this is a car wheel, aluminium alloy wheel, which I have plated with nickel, an example. And some of the examples I have plated with nickel and chromium on aluminium rods. And this is a pipe, hollow pipe. So I'm giving you some examples of what has been done. So claims the prior arts disclose different methods to deposit nickel on aluminium. However, there is no simple method that enables nickel to be plated directly onto the aluminium oxide layer. That is the challenge. I have started by doing the practical first, showing that it can be, aluminium can be plated with nickel, but I did not have the theory behind it. And when I did my PhD some 35 years ago, I had problems with the oxidation of aluminium, and my supervisor, PhD supervisor, said, look, what you have invented is either rubbish or it is something new, and material science, a new branch of material science that I do not know of. So it took me 30 years to understand the oxidation of aluminium. And then I found a paper by Professor Mott, M-O-T-T. He was a professor in Cambridge, and he got Nobel Prize in physics. And he said that he had a theory, a model of oxidation of aluminium. And that model, at that time in 1947, he produced a model for that. And at the end of that paper, he says, I do not have an instrument to prove my model. And I had worked for Philips in the 1980s. And what I have found, I've discovered or made an instrument which was showing the results of Professor Mott's work. And I said, look, he had said that he doesn't have an instrument to prove his model, and I have the instrument which proves his model. So however, my PhD was through, but I was not very happy to understand what really happened, the real oxidation of aluminium. So I'm not going to go into his theory. So then I was in Malaysia, so I did apply for a patent. And electroplating is classed as the bottom up method for preparing nanocrystalline materials. This is one step because you do the electrodeposition, and we don't have any more things to do. As it deposits nickel on the surface of aluminium, that nickel, by virtue of its deposition, is nanocrystalline. We do not need to do anything else. We do not have to do a heat treatment. We do not have to do any other processing to convert that into nanocrystallinity. So, and the particle size are less than 100 nanometers. Some of the electroformed things that that can be done. Electroform means it's a forming process using electrodeposition. Some of the silver components and many other things can be done. So I'm not Can you hear me now?
Yes, sir.
Okay, so I got disconnected. Sorry about that.
Yeah, no issues.
Yes, sir. Your voice is now audible, sir.
Okay, I can't move my slide. Okay.
Sir, but
Can you see?
but your video is not visible, sir. Your screen
Sorry?
is not.
Sir, we are not able to see your screen, sir. Share your screen, sir.
Share the screen. Mm. Goes away. Is screen sharing gele chole jete sida. Ignore korte parteche. Eta
Sir, minimize your PPT. Then you can see the share screen button, sir.
Sorry?
Minimize the PPT, sir. PowerPoint presentation.
So no, I need to. Or can you see me? You can't see me. Yeah. Dekte parteche na. Eta সরাইতে পারতেছি না তো।
Yes, sir. We can see your screen, sir.
সরাইতে মুভ করতে পারতেছি না তো। Okay, so I have to move from there. Sorry about that. Okay, so this is slightly my apologies. Thanks. It's quite, nobody's here to help me. There's no technical backup. It's 6 o'clock in the morning here. Synthesis of nanocrystalline. Oh God. Oh, I can't move it. Oh, okay, fine. There is a company called Vico Precision. They specialize in nanocrystalline materials. They can make certain things. So I'll show you that Electro Forming and additive manufacturing, atom by atom. They do a lot of manufacturing in their own world. So if you want to have a look at this in your own time, you can have it. It's called Vico Electro Forming. They do a lot of work on, let me, if I can, oh God. Where am I?
Your screen is not visible, sir, now.
Screen not visible.
So now your screen is not visible, sir.
Yeah, I realized that. I'm trying to come back.
Oh, okay, okay, sir. Okay, sir.
I shouldn't have come back there. Oh. কিন্তু এটা তো আমার এখান থেকে টিপ দিতে হবে তো এনতেই যেতে পারতেছিলাম তখন ছিল তো Can you see me now? Hello?
Oh, yes, sir.
Okay.
Yes, sir.
Okay. So I'm showing some slides now, the synthesis of nano nickel cobalt nanorods. What I've done is I have plated on the surface of aluminium and then I peeled them off on the surface, right? This is an aluminium piece plated with nickel. So what I've done is I peeled off from the surface of aluminium this is nickel plated on it. Now, I have a professor in America. She's working with me. So she had studied the peel surface. This is the surface, the coating. I don't know if you can see. This is the outside and this is the inside. So we looked into the inside of this material. And we found that there are plenty of nanorods and nanowires on this structure. So you can see that this is an atomic force microscopy images. And you can see that there are plenty of nanorods and other things in it. And this is about 46 nanometers. And you can see this nanotubes here. Looks like a tube, which has got a diameter of 42 nanometers here. So we've got plenty of things, which was something which I did not know of. So this is by depositing nickel onto the surface of aluminium, that was not my intention to prepare nanorods and nanowires. But it happened as we did the characterization of materials, we found that we have produced something, a miracle, which was not existing. And so if you look at the surface of aluminium, one thing I used to think that there must be some porosity on the surface of aluminium. This is aluminium anodized. But many years ago, my knowledge about the surface of aluminium was not very good. So I used to think that there are porosity on the surface of aluminium. And as I pumped a nickel solution through, as you see across here, the solution went inside the pores and it deposited nickel, which is completely wrong. If you, some people say that high-speed deposition, this is, I'm not going to talk about, this is called a jet electroplating, where you have a cathode, small, tiny, which is less than 1 centimeter in diameter, and you pump solution straight onto the surface here. Say if it is nickel electrolyte, you're pumping the solution at a very high speed, much higher than mine, but it is used for only electronic materials, which is few tiny millimeter size. But my one is not high-speed jet. I can plate, as I've shown you, any big surfaces, not only tiny surfaces. So it is some people, when I published my paper in 2012, I'm a fellow of the Institute of Materials Finishing in Birmingham, UK, and they said my process is jet finishing, and which they didn't even understand at that time. So the difference between turbulent flow electrodeposition and electroflow and high-speed jet flow. So I'm not going to go into that one. So this is some of the high, this is SEM, scanning electron microscope, at a high resolution microscope. I can see that this is only about 120 times magnification. I call it like a cauliflower structure, and it is slightly higher magnification here, which is times 200, which is slightly bigger. And as you go into 350, one thing I would like you to appreciate that you see there are no cracks, no openings. This is continuous growth of nickel onto the surface of aluminium. There is no cracks or anything in it at all. So that is something very unusual. So it is a full, complete coverage of the metal. Now, as you go higher, there's some, this is if you know about electron microscopy, now we've got some glittering here because of the charging as it happens. So this is 350, we go higher. This is 15,000 magnification. You can see that the depositions are growing layer by layer, and on top there's something else happening. So this is 100,000 times magnification of the same surface. And you can see that some of the particle size are 37, 32. So these are high resolution electron microscopy showing the presence of tiny particles of nickel on the surface of aluminium. So this is nanocrystalline. And then this is transmission electron microscopy here, TEM. And you can see that it has picked up the nickel particles as small as 6 nanometers here, there are 4 nanometers here. The particle size of nickel is really tiny. So what I've said, high-speed turbulent electrolyte flow has been used as an innovative process for directly depositing nickel on aluminum surfaces without the need to pre-treat the substrate with acid or anything else. So I'll quickly move on to the other place. And then we do adhesion tests, and there are certain tests for testing the level of adhesion between the aluminium and nickel. So this is some of the adhesion tests. So for example, we can put a sellotape, a tape on top of the plated metal, and then pull it. Very simple process. If in the pulling, if you put a tape here and then you pull it, if the coating starts to peel off, that means your coating has got a poor level of adhesion. I can show you some of the samples here. I don't know if you can see it. So you see these samples are really adherent. There is no break or no peeling off from the surface aluminum. This side is aluminium. This side is aluminium, which you've got a red writing here. And on this side, on my left-hand side is aluminium. So the level of adhesion is excellent. So what is, I'm going to talk a little bit about nanomechanical testing. I don't know if you know much about it. This is a material property tester. We test the hardness of material by putting an indenter on the surface of a metal. The soft metal goes down. So this indenter here, we put it on the, say, for example, it is high carbon steel or something, maybe for example, and this is a softer metal. So we put a load. As we put the load, it goes inside. So there is an indent here. So that indent means it's not elastic region. It is in the plastic region. Plastic means if the metal has deformed permanently, it's not going to come back. So when you pull a rubber, something like that. Pulling, it increases, but when it take the load off, it comes back to its original position. If I bend it, it will not break. So this is a permanent deformation, and this is how we measure the hardness of a material. And different ways of measuring hardness, Ficus hardness. So this is, I'm not going to say too much about it. Only thing is that these are the soft metals showing the hardness. We measure hardness by using indenters. Now, in terms of nanomechanical testing, we have a special indenter, which is at nanoscale. So you can put this indenter on the surface of the nanocrystalline material, and you can make different indentations. But what interesting thing is with nano indenter, so for example, if you can look at my hand, when I put the indenter onto the surface, now this is in the elastic region. So when I put the indenter, the metal is curving, but it is not in the plastic region yet. It is still in the elastic region. So when I move my hand slowly, the metal will come back to its original position because it is in this elastic region. Now, in the previous one, we couldn't do the measurements of elastic properties like tensile and other properties. Now, if we have a nano indenter, we put the indenter, you can see this is the load and this is the depth. This is the depth. So as you put the indenter is going inside the metal, and we go up to a certain limit, still within the elastic region. That means the metal hasn't deformed permanently. So it is not in the plastic region. So then what we do, we take the load off and the metal comes back to its original position. And that gives us measurement of the hardness, and we can also measure the tensile properties from there, which is an excellent way of using nanomechanical properties of metals. So this is how it is done. Now, I did a cross-section of aluminium. For example, cross-section means if I have two metals, can you see two metals here? So I've got two layers. One is nickel and the other one is aluminium. So when I did the nano indentations, you can see that this is the hardness or the load on this Y, and this is the depth of the indentation. And you can see that nickel is definitely harder than aluminium. Aluminium is softer, so the indents have gone in quite deeper into it. So this is an indication that I've got two different layers of metal, which is nickel, deposited on the surface of a soft metal, which is aluminium. So without going deeper into it, then we can, with this nanomechanical testing, we can find coefficient of friction, wear cycles, many things, which is much different than the normal materials properties we use for many other things. So with this, this is an interesting thing. This is a nickel. As you can see, this is much harder. The load is, it has taken more load, and aluminium is this one. This is the curve for aluminium as you take the load off. And so there's a big difference between the nickel nanomechanical test indentation modulus. There's significant difference between these two. So what we did, let me go back here. So you've got different layers. So the indentations have gone from 1, 2, 3, 4. So we've got layer of nickel and aluminium going across. So what you could see here, that this is the indentation, Young's modulus, and then you can see that this is hardness here, and the modulus is different. As you go from nickel to aluminium, the differences are quite different. You can see that there is a change at the interface. And remember this, this will be required as you go into next few slides, that there is a significant difference. Say it's 5, it is 200, and it is 80, and there is an interface. As they have gone from nickel onto the aluminium or aluminium to nickel, there is a change in the data. You can see that, okay? Both in the hardness and also in the properties here. So, and this is a very expensive transmission electron microscopy images here, which I've got it done from NUS, National University of Singapore when I was there. I had lots of money. I got about maybe $1 million to carry out my research. And they had, at Malaysia, we didn't have the instruments I needed. So this was done in Singapore. So you can see that I have, as I showed you, I've got a layer of aluminium coming from there. And then there is an interface, which I showed you in the last slide. There's an interface and there is nickel here. So there is an oxide layer. So did I plate nickel onto aluminium with the oxide layer? That was the question. But regardless, I plated with very high level of adhesion. And then I have got more nanomechanical testing results here without going into it. So you can see that layers of indents. So there's stainless steel, this is stainless steel and nickel. Reduced modulus, which is the tensile properties, and hardness. So near the grids of indentations were performed at 10 to 14 newtons. And near the interface, the hardness of the steel increases. And then there must be some hard intermetallic compounds to be confirmed by EDX. And okay, so let me go from here. So let's, I'm going to give you a theory now. This is one of my master's degree students. He was keen on this studying the surface of titanium. So we did a lot of work on sample preparation. As you know, TEM is transmission electron microscopy, is quite hard work. So he made the preparation. And from this image, you can see that it looks like there are some porosity on the surface. Is it a porosity? From his work in 2010, I said, well, to me, it looks like porosity. And he wrote in his thesis that titanium has got porous surface, and aluminium and nickel has been plated on the porous surface, which is incorrect. Now, recently, I've been in touch with a professor in MIT, and he has published a paper which shows that this is the aluminium oxide. Can you see this? I can't see it properly. And this is aluminium oxide. This is schematic diagram. I'll show you a video soon. And you can see that what he has done, he has used a special instrument called environmental transmission electron microscope. And I understand there are about 10 in the world at the moment. I haven't used it here. So he has got access to transmission electron microscope, which is called environmental one. So what he did, he went into the oxide layer and he managed to break. This is the oxide layer. This is aluminium. As I said, the aluminium is covered with oxide layer. So this oxide layer is non-conductive. So for that reason, if I put nickel here, there will be no plating. That's the reason we can't plate on aluminium, because aluminium is protected with this thick oxide layer. Now, what he's done, he's been able to pump oxygen by breaking open the oxide layer. Can you see that? So this is the oxide layer. It started with this one. There's no break in the oxide layer. So he has produced a pressure on the surface of the oxide. I cracked it open, I pumped oxygen through it, and you can see the oxygen has gone into the grain boundaries of aluminium. And then there's a crack. Now here we go. So in my case, what I have said, that aluminium has got an oxide layer. And if you remember, I said I'm pumping solution at a very high speed between the anode and the cathode. The solution is pumping at a very high speed. And I have put a lot of pressure, which is a potential between the anode and the cathode. So in my case, what I will say, or my hypothesis is that I have been able to crack open the oxide layer. And if when the nickel solution goes from, say, from left to right to left, going to the left. So if it is able to crack open the oxide layer and it sees pure aluminium. So if I can see pure aluminium, nickel sees pure aluminium containing Ni2+. So it will deposit nickel here. So wherever there's a crack, so as the solution went past the surface of oxide layer, it cracked open the surface and now it has made aluminium. So if we can deposit, if you have pure nickel here, nickel will be deposited here. So I have been able to crack open the oxide. So only recently, this professor spoke to me and said, what has happened here is you have cracked open the space between the oxide layer and the aluminium. So you've been able to plate aluminium with nickel. So this is, I don't know if I'll be able to show you the video. Let me. This is at the 5 nanometer scale. You can see this is the oxide layer. I'll play it again. So he's breaking the oxide layer, as you can see that interface. And then, can you all see it? This is the pumping, and he's trying to break open the oxide layer. And we successfully break the oxide layer. So basically, these are the grains of aluminium with oxide interface, and we have been able to. And he has, using his electron microscope, he's been able to break open the oxide layers from the surface of aluminium. So aluminium was scraped of the oxide layer. So this is at a very fine layer of about 5 nanometers and less than 2 nanometers. And the oxide of aluminium is about 2 nanometers thick. So, and he's working in this nano scale, which I do not have access to. How do I get out? Okay, so I'm coming to an end of my presentation. My apologies for the problems we had. It has been possible to electrodeposit nickel directly on the surface of aluminium without any pre-treatment process, using a very basic power supply and without any additives. Generally, if you want to deposit nanocrystalline nickel, what they do is either produce different chemicals and change the electrochemistry of the nickel solution, or they use some additives to make the nickel grow slowly. And as plated, nickel is nanocrystalline. But in my case, I have used high-speed turbulent flow mechanism to deposit nickel on the surface of aluminium, which is an oxide-covered material. And what I have done is use nanomechanical testing to show nickel aluminium oxide layers, and they have different modulus and hardnesses. Modulus means tensile testing. We do it, as you know, as you pull some metal, we call it tensile testing, and we've got compressive testing, and we've got another properties which we choose to test metals. So in my case, I've used at nanoscale nanomechanical testing, which is very expensive equipment, as I have access to the machines in Saudi Arabia and also in Singapore. So I have been able to use those machines. So what the final conclusion of my research was, nanomechanical tests show nickel aluminium oxide have different modulus. However, the oxide layer is much softer. As I showed you in my nanomechanical layers, as it went from nickel to aluminium, the aluminium was softer. And there was an interface as it goes from nickel to aluminium, the interface, the hardness and modulus changed as it went from nickel to aluminium. So it shows that inconsistency properties, which indicates that the natural oxide is responsible for these inconsistencies. This was written before I did my the professor's breaking the oxide layer. So now obviously the oxide layer of aluminium is much softer, and that is the reason why in the video I showed it was possible to break open the oxide. So by pushing through the oxide layer, it was possible to break open the oxide. And then as you break the oxide layer, my nickel solution just went inside and locked, and it was possible to plate nickel onto aluminium. It's very difficult to present information on the videos. And thank you for listening to me. If you have any questions, you can fire away, please.
Thank you, Professor, for making us understand the concept of electroplating. We really enjoyed your lecture.
Actually, it's breaking. I can't hear you. It's breaking.
We really enjoyed.
Okay, thank you. Thank you. I hope it is difficult to demonstrate things on here.
The thing is,
but
we have demonstrated the functional behavior of the material that we have prepared. That was the unique feature of this conference, I think. You have shown, you have displayed, or you have shown all the material that you have prepared by this method. That is the wonder of this conference. Professor, I have two questions regarding the electron potential. For this case, what is the electron potential? You have not mentioned it. Electron potential value, is it more or less than the conventional method?
We don't measure electropotential. What it is, between, let me go back. Yeah. What it is, generally say we use, we call it amps per decimeter squared. So generally it's a quite low current density we need to pump nickel out of anodes here into solution there. But here I am able to increase the potential 10 times, and that increases the rate of plating. So generally, if you're plating normal nickel on like we do in steel or copper and other things, the rate of plating is about 50 to 60 microns an hour, using a small potential between the anode and the cathode. But here, I increase automatically because of the closeness between the anode and the cathode, the current density increases, potential increases on its own. So that increases the rate of plating. So when I invented that machine, that equipment I showed you, it plated about 2,000 microns an hour. From 60 microns an hour, it went on to 2,000, up to 2,000 microns an hour. So it had.
I think this is one of the advantages of this method.
Sorry?
This is what are the advantages of this high-speed electroplating?
I didn't understand it. It's not clear.
Advantages of this high-speed electroplating methods.
High speed, yeah. The rate of deposition increases as I increase the solution flow. As I showed you, I pump the solution between the anode and the cathode. It moves there, and as the solution moves quickly, the potential increases, and I'm able to increase the potential many times more than here. Here, you can't really, if you increase the potential as I have increased here, which is the voltage, current density, this will burn. This will become black here. If I use the same amount of current, which I've used here, this will completely churn. It will be black all over this place. So as the solution moves, it takes, every time it comes back and you've got a fresh solution here. Whereas when you're plating here, the solution is the same. You know, you don't get new ions. It's a whole ions are, with time, there is some hydrogen will be covering the surface here. So it will not let new nickel ions deposit here. So in this case, there is no hydrogen stagnancy. So it will just move quickly. So
will it be cost effective?
Yeah.
Will it be cost effective?
Oh, definitely, yes. I mean, if you think of that plating on aluminium, you can't do it. So you can do it completely. Now, as I spoke to British Aerospace, no, what is Airbus, isn't it, in Europe? When I speak to these people, that can you plate aluminium with nickel? Well, yeah, we can do it. I said, okay. So how do you do it? Oh, I said, can you plate them directly? Yeah, we can plate directly. But I'm talking about Airbus. And then I said, do you put a layer of zinc? No, yeah. We put a zinc first, and then we do nickel plating. So if you think that there are many applications where you do not want any layer of zinc between aluminium and nickel. In my case, there's no zinc, there's no other metal, it's pure nickel onto the surface of aluminium. And the aerospace, Boeing, Airbus, and there are many, and even titanium. I had a friend, a colleague I worked with, he was doing a master's at Cranfield University with me, and he was F7 pilot, and he said, you know, when you've got a titanium body airplane, you have got less than 1 minute to eject. So there is a need for plating nickel onto titanium as well. And what I haven't been successful is plating on magnesium. I plated stainless steel, plated titanium, aluminium. I've tried magnesium. As you know, magnesium is a very reactive metal. As soon as you put it inside this, as soon as the solution touches, it sort of goes black. So I haven't been very successful in doing. If I have future students, maybe someone could try plating on magnesium. So for now, it is important because it's not the money. There's a need for plating nickel onto aluminum surfaces without any interface. And it is cost effective. I mean, it didn't cost me a lot of money to do this. It's a very simple process. So to answer your question, it is cost effective, but we need to change a few certain things. But I haven't done it on a commercial scale as yet. I've done it on a small scale.
Thank you for your nice interpretation. Any questions from the audience, please? Participants, delegates, if you have any question, please raise your hand. Professor will respond to your question, please. If there is no question, then we can wind up the session. We have next session by 11:30. Any questions? Since no questions from the delegates, I thank Professor for giving a very wonderful lecture. It really makes us to feel the physical presence. You have delivered a lecture in our land. It felt it's thank you for your acceptance to participate in this conference, which is conducted in the blended mode. Thanks for accepting our invitation to give the inaugural address as well as the lecture. Thank you, sir. On behalf of the organizing committee, we thank all the participants.
Thank you.
Yes.
Thank you, sir.
Is there? Yep. Carry on.
Thank you, sir. A charming and a cherished personality of our department and a teacher.
Bismillahirrahmanirrahim. Dear present, good morning. One and all gathered here in the ritual now. I feel honored and privileged to get an opportunity to propose a vote of thanks on this inaugural function of International Conference ACI CR 2022. On behalf of our organizing committee, first of all, we express our deep gratitude, our most respected secretary and correspondent for his constant encouragement, ceaseless support, guidance, providing a stimulating environment for such educational development. It is his vision and leadership that has brought revolutionary changes in our institutions. Thank you, sir, for your valuable presence and a constant support to conduct the conference successfully. We express our sincere thanks to our esteemed President, who is a wise and gentleman and a source of inspiration for all kinds of activity. We are very grateful for his valuable presence for this occasion. Thank you, sir, for your constant support and guidance for all activities of our department. Next, I express my heartfelt thanks to our respected Assistant Secretary, who is an ever-smiling personality and a high-hearted person. We are very grateful for his valuable support and a constant support for all kinds of activity as well as our conference. Thank you, sir. Next, I wish to express our honorary director and the director of various hostel administration for their kind support to conduct a conference in successful manner. Thank you, sir. We are extremely grateful to the most distinguished chief guest, Professor Dr. Mohamed Sakawat Hussain, DL, Principal, College of Science and Engineering Management, London. Sir, your name is Sakawat. Sakawat means that is a magnanimity. Really, you are a very magnanimity and a generosity to have accepted our invitation for inaugurating the conference and deliver the inaugural address. We are grateful and encouraged by your gracious presence and immensely benefited by your inspiring inaugural address and a keynote address on high-speed forbidden electrolyte flow electrode deposition. Thank you, sir, for your illuminating address. Silver is a shining metal. It is a good conductor and it is a very brilliant white metallic cluster we know very well. Similarly, our principal is a shining star of our college, who is acting as good conductor to conduct all kinds of activity in his right direction in a successful manner for his meticulous planning. On behalf of our organizing committee, we express our sincere thanks to gratitude to our Lord Principal for his ceaseless guidance and constant support for all activities. We are inspired. Thank you, sir. We express our sincere thanks to our Vice Principal for his constant support and available presence for this occasion. We express our sincere thanks to our head of the department and additional Vice Principal, Dr. M.S. We know very well Dr. M.S. He is a M.S. man of silence, man of simplicity, as well as man of spiritual, who is acting as catalyst for all kind of activity, and he has been an inspiration to our department and relentless support and success all kinds of activity. Thank you, sir, for your catalytic action. We record or acknowledge our sincere thanks to gratitude our Lord Professor from our college and its sister institutions. Most of the delegates from the various countries like Bangladesh, Odisha, and other states for their valuable presence for this occasion in the virtual way. Thanks to everyone for their valuable presence for this occasion. This day would have been meaningless without the presence of our delegates. The delegates are the nucleus of the conference. We wish to express our profuse thanks to all distinguished delegates who will come from different places and the various countries and states to attend the conference in the virtual mode. This reflects a commitment to the profession. Thanks to everyone for their valuable presence for this occasion. And even cannot happen overnight. The wheels start rolling few months before. the big wheel rolled by a small axial pin. Yes, our convener Dr. S.K. Berisami, organizing secretary, acted as axial pin. That means, you know very well in Tamil, Cyril Achani, which rolled the big wheel. So he rolled the wheel in the successful direction, and on behalf of our organizing committee, we record our appreciation and thanks to you, sir. Finally, we wish to place record our hearty thanks and appreciation to our all my colleagues and non-teaching staff and our first MSc and the second MSc students, especially Mr. Ashraf Ali, Narendran, Chandru, and Mohamed, and from first year Raghunath, all, so they are very efforts to conduct a conference. On behalf of the organizing committee, we appreciate and we thank to everyone to conduct a conference in successful manner. Once again, we thank you all. I am always telling about chemistry. Chemistry is good. Chemistry is good when we love with it. Chemistry is bad when we crack with it. So we love the chemistry. Thank you.
Now it's time for tea break.
Thank you, sir. Now it's time for tea break. Refreshment is provided for the participants. I request everyone to have refreshment and assemble in the hall by 11:25.
Sir, good morning, sir. Anandam, sir. Sir, good morning, sir.
Hello.
Sir, sir, good morning, sir.
Good morning. Good morning. Because my video and audio was unmute, that's why I could not able to.
Okay,
talk.
okay, sir.
Yeah.
Sir, we start the program within 5 minutes, sir. Please.
Yeah, yeah. So I will check.
This is the enter screen.
I have to select.
Yes. Share. So now it will.
There is something. Is it visible?
Yes, sir. Visible, sir.
Sir, yes, sir. Visible, sir. Yes.
The slides are moving.
Yes, sir. Moving, sir.
Right? Moving.
Yes, 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 sir. Yes, sir.
1 minute. So that video also can be able to do that?
Yes, yes, sir. Yes, sir.
Okay. So,
Everything is correct, sir. Perfect, sir.
One also I open it.
What is the first video? This one or
that one?
Hyderabad-based ARCI, an autonomous institute under the Department of Science and Technology, is conducting.
Okay. So first I have to display that video. That I open. Huh? After that I will open this. Okay. Next I have to see that run that video.
Then back to this folder.
Where?
I just crossed it.
Okay, okay. Understood.
Doesn't yaar inga illa pasanga.
Technical session 1. I hand over the session to technical session in charge Dr. A. Jafar Ahmed sir and Dr. S. Sayed Abudaki sir. I kindly invite Dr. S. Sayed Abudaki sir to give brief introduction of each test. Please, sir.
வந்து வீடியோ ஸ்டார்ட் பண்ணுமா ஸ்டார்ட் வீடியோ கொடுத்து மக்கள் கூட்டத்தை காமிச்சாங்க ரொம்ப கம்மியா
Sir, why is this audio, sir? 3,000, sir.
Hello.
Yes, sir.
Yes.
Bismillahirrahmanirrahim. Assalamu alaikum and good morning to all present here. On behalf of the Department of Chemistry, Organizing Secretary
So now,
the 7th International Conference on Innovations in Chemical and Environmental Research. I need Professor Mohamed and to introduce the today's resource person of this technical session. Dr. M. Srinivasan Anandan, sir.
Just make it up.
Sir is working as a scientist in Center for Nanomaterials, International Research Center for Powder Metallurgy and New Materials, Hyderabad.
Go there.
Sir did his UG in Varanasi University, Tiruchirappalli. After that, he completed his master degree from our college. Sir is an illustrious alumnus of our department. Then he completed MPhil from the same Varanasi University, Tiruchirappalli. Then he is awarded PhD program during the year of 2003 to 6 from Anna University, Chennai. Then Sir worked as a postdoctoral fellowship from 2006 to 9 in National Institute of Material Science, Japan. Then he worked as a fellowship in Japan Society for Promotion of Science. From 2012 to till date, Sir is working as a scientist in International Advanced Research Center for Powder Metallurgy and New Materials, Hyderabad. Sir received nearly 15 awards in aspect of Best Paper Presentation Award, Young Scientist Award, JPS Fellowship Award, Best Outstanding Award, and so on. Sir field of interest is to develop the material to store the energy, because today we are using the storage material in the form of battery. Sir is mainly focusing on the particular area. Then he received around 7 patents. Getting a patent is not an easy task. Sir almost granted 7 patents. The Sir published 2 book chapters and he published proceedings in international conference. He delivered invited lecture in 21 field in national and international conferences held across the nation. Sir published 68 research articles in national and international journals which having high impact factor. Then Sir published 4 articles in magazines and newsletters. He guided 2 PhD scholars under his eminent guidance, and currently he is doing 2 scholars are doing research under his guidance. Sir guided 4 trainees. Sir participated in 65 conferences held across the nation, across the country. So the list is going on. So such a nice person today we have. I request all the participants kindly make use of this short valuable session. So with these viewers, now I request Dr. Srinivasan Anandan sir to deliver the invited lecture. Yes, sir.
Yeah. So, Professor Periyasamy, my screen is visible?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Visible, sir. Visible, sir.
Yeah. Moving, right? Slides are moving.
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay. May I start my presentation?
Yes, sir.
So, very good morning to all of you. First of all, I would like to thank Professor Periyasamy for his kind introduction about me. And at the outset, let me thank Professor Sigabuddin, Additional Vice Principal and HOD Department of Chemistry, Professor Jafar, Professor Periyasamy, and other organizing committee members for inviting me to deliver a lecture on this international conference. Being a Jamalian, I am very glad to be part of this event. And I really congratulate the entire team to conduct such an event on regular basis, which is useful for that scientific community, particularly it is useful for that student. I wish the department to conduct that international conference in future as well. The title of my presentation is Design, Development and Demonstration of Advanced Nanostructured Material for Energy Storage application like lithium-ion battery and then supercapacitor. As all of you know that lithium-ion battery, we are extensively used in that electronics as well as that vehicles. So there is a huge requirement for this, the technology, lithium-ion battery technology. Considering the current scenario, unfortunately, we don't have any single technology for this lithium-ion battery. So in order to make India self-reliant in this particular technology, development of indigenous technology for the development of material as well as self-fabrication is need of the hour. ARC is one of the premier institute. We have been working on the development of materials as well as self-fabrication technology related to this lithium-ion battery. And then I'll be presenting in detail about that R&D activities which we are doing at ARCA. Before my presentation, I would like to rewind my journey at Jamal Mohamed College. I was doing my master at Jamal Mohamed College during the year 1999 to 2001. So Professor Abdullah Basha, he was my principal, and I'm very thankful to him for giving opportunity to study at Jamal. And I'm extremely thankful to all my chemistry faculty, starting from Professor Bashir Ahmed. He was my HOD. And I thank Professor Janai Raman and Professor Fashal Ahmed. He was my project guide. He is a very nice gentleman to work and then down to earth person. Professor Jamil, Professor Siddiq Ali, and Professor Qasim. I would say that they are stalwarts and in their respective subject, and they are most respected professor. The way they have commented on that during the class, it was amazing. I'm extremely thankful to all my beloved and respected professor. And then I have listed out other set of professors, starting from our Professor Sihabuddin, who is heading that chemistry department now, Professor Sini Mubarak, Professor Jafar, Professor Nasser, Professor Badusa, Professor Burganuddin, Professor Zahir Hussain, and Riyaz Ahmed. When I did my masters, they were kind of young faculties. Now I am very happy to see them that they are leading that the chemistry department, and the way they are sustaining that legacy left by all that stalwarts of the previous professor. It is amazing to see that the progress of chemistry department. When I refer that chemistry website, I have seen that more than 110 PhD students have produced so far, and more than 300 MPhil students are produced. It is kind of amazing number. And another surprising for me, 3 patents comes out of chemistry department. Being an academic institute and then doing R&D related to all this invention related, it is not easy. So this shows that how sincere, how they are passionate towards research. So I wish them, and then I am very sure that they will take that chemistry department into the greater height in the near future. It is kind of very small tribute to our the professor. The lesson taught by this eminent professor have given us indispensable knowledge and guidance throughout our college days. So the sincerity and dedication they have shown that towards the development of college as well as that nurturing young talents, it was amazing. It is their hard work and passions which have helped in producing bright student who is doing well in various positions. When I used to discuss with our Professor Jafar sir, he used to tell our Jamalian, they are holding very good position in that ISRO and other leading national R&D laboratories. It is all because of our professor. They have given their support, encouragement, and motivation. In my case, I proudly say that what I am today is, it is because of all this professor guidance and support. And their service is highly respected. And I am very grateful and thankful to all my beloved professor. And I pray God that they have to lead a healthy, peaceful, and then happy life. Further, I thank that the management and Professor Ismail Muhaid principal for giving me opportunity to present in this international conference. And I also wish all that young faculties from the chemistry department concentrate on that the progress of the department, and they will take that department into that next higher levels. With this, I will start my presentation. So I would like to give brief introduction about ARCI. ARCI is International Advanced Research Center for Powder Metallurgy and New Material, which is a premier autonomous R&D institute, comes under Ministry of Science and Technology. So ARCI has in operation of 11 centers of excellence. Nine centers are located in Hyderabad and 2 centers are in Chennai. So the unique mandate of ARCI is we work on the development of new material or novel process. And then we work on that upscaling of whatever the developed process in the R&D level to produce large quantity of material. And if it is material, we work on that fabrication of prototype. Once we prepare that the prototype, we demonstrate it for real application. Then we go for that transfer of technology to that industry. Simply saying is our main focus is translation research, where we convert that basic R&D research into that the technology. I work in Center for Nanomaterial. Our center mainly focus on that application-oriented research, which is relevant to Indian needs and condition, as shown in the chart. So that our center mainly focus on the material development for water purification, textile self-cleaning application, strategic sector, automotive, material for alternative application, and then nanocomposite. In each case, we work on that lab scale R&D, specific application targeted based on that the R&D what we have done at lab scale research. So the another thing I would like to highlight here, when you are doing research with the relevance, the impact is always high. So when you want to take that your lab scale R&D into the technology or product, you should have kind of multidisciplinary. It is not only about the science. There are a lot of engineering aspects involved when you are going for that prototype fabrication or designing the reactor. So that multidisciplinary expertise is required. And also the discussion with the collaboration with the industry also, it is required to know what are all the requirements when you are taking your lab scale level into that product or technology. These are all multidisciplinary research is required to take that basic R&D into the technology level. This slide shows that outline of my presentation. I will start briefing what is the energy demand and the statistic about the energy consumption. And I will highlight that what is the importance of energy storage device and the application of lithium-ion battery and then supercapacitor also it covers. And then mainly I will be covering that R&D activities which we are doing at ARCI. So this slide shows that the various energy sources, the fossil fuel sources available for that energy generation. As you can see that in the pie chart, major contribution coming from that coal, natural gas, and then oils. The main issue is these sources are available only for limited period. For example, oil, it is available for 30 years, natural gas 60 years, and then coal for 200 years. But if you can see the energy requirement, currently we have the energy requirement of 13 to 15 terawatt per year. When it goes to the 2050, our requirement is nearly 30 terawatt. But the issue is we have only limited fossil fuel sources available. Other major issue, when you are burning all this fossil fuel, it is emitting a lot of CO2 and then carbon footprint keep on increasing, which leads to a lot of global warming issues and all. As per statistic, we are the 4th largest producer of CO2 in the world. And then 1.34 million metric tons we are releasing into the environment. So there are two issues we have to address. One is the fossil fuel sources are limited, which cannot meet the energy requirement. Another one is when you are burning that CO2, which normally we are using all that the petrol, diesel for the transportation. When you are using, it is emitting a lot of CO2. You have to find an alternative way to run that vehicle. Electric vehicle is the one option where you can minimize that CO2. there are some other advantage also it is there. I will cover that. So mainly depletion of fossil fuels and increase in energy demand and then large CO2 emission are forcing us to look out that alternative energy sources. As all of you know that renewable sources like solar and wind, tidal mill extensively used for that energy generation, and it is available forever. You don't need to worry about that the sources. Once you generate that energy from all these renewable sources, you should have kind of proper energy storage devices. Lithium-ion battery and then supercapacitor are considered as the promising energy storage devices because of its unique characteristics. Lithium-ion battery and then supercapacitor both are having its pros and cons. For example, lithium-ion battery can store more energy, whereas lithium-ion battery, the supercapacitor, it can fast charging. It is possible with the supercapacitor with the long cycle life. So the mechanism is different in both cases. Lithium-ion battery operates with the Faradic reaction. Supercapacitor operates with the non-Faradic reaction. These slides, I would like to give that a basic introduction about the lithium-ion battery. A battery is a transducer which converts the chemical energy of its active material into electrical energy through electrochemical reaction. That Faradic reaction, it involved in that the battery. So it is classified into two battery. One is primary battery, which is not rechargeable. Another one is secondary battery, which is rechargeable. All our mobile phones, laptop, and then electric vehicle, we are using that secondary battery. If you can see the components of a lithium-ion battery, there are four important components are there. The anode material, usually that the graphite-based material used as a anode material. When you are mixing with the binder and the conductive carbon, you can make that a nice anode electrode. Similarly, in the cathode, lithium-based compounds are used as a cathode material. When you are mixing with the binder and the conductive additive, again, you can fabricate that the cathode electrode. And then third important component is electrolyte. So lithium salt, which is dissolved in that ethylene carbonate or diethyl carbonate, used as a electrolyte and used as a ionic conductive medium within the battery. And then the separator, which is used as a kind of to avoid the short circuit between the cathode and the anode. Separator is placed between them. And then usually that the polymer-based film are used as a separator. As you can see in the figure, all high voltage materials are cathode material, starting from lithium manganese oxide, cobalt oxide, and then LFP, and then lithium vanadium oxide are extensively used as a cathode material. And the low voltage material, usually that anode material, starting from that graphite, tin, germanium, silica, are used as a anode material. You may ask what way that lithium-ion battery is having advantages over the other secondary battery which is available in the market. If you can see the characteristics like energy density, cell voltage, and the operating range, self-discharge, cycle life, it is much superior than that other secondary battery. For example, if you can see the energy density of lithium-ion, it is about 150-250 watt-hour per kg. Whereas the other secondary battery, not even 100 watt-hour per kg. So in terms of electric vehicle, if you have the more energy density, you have more driving range. If you have the less energy density, you have that less driving range. So when you are using all that lead acid or nickel metal hydride, the driving range, it will be less. That is the disadvantage. So every time after 50 kilometer or 100 kilometer, every time you have to do the recharging. And then because why that energy density is high means the cell voltage of lithium-ion battery is about 2.5 to 4 volt, whereas other the secondary battery, the voltage is less. Similarly, other characteristics like cycle life and then high power performance, all it is high compared to that other secondary batteries. This slide shows that the history of lithium-ion batteries. So Professor Whittingham, first he invented the first lithium-ion cell in 1978 using lithium titanium sulfide as a cathode material, using lithium foil as a anode material. So even though he is successful, but the voltage, having said in previous slide, if the voltage is less, the energy density is less. So what Professor good enough. What he invented is, he invented lithium cobalt oxide, which is having that voltage of around 4 volt. Once the voltage is higher, your energy density also is high. And then still he uses that lithium foil as an anode material. Handling lithium foil is very difficult because it is highly flammable. You should have kind of specific condition to handle that lithium foil. So to address that issue, the Japanese group led by Professor Yoshino, they have replaced that lithium foil with the graphite. So this is what the invention of lithium-ion battery happened. Finally, Sony commercialized first lithium-ion battery in 1991 using lithium cobalt oxide as a cathode and then graphite as a anode material. And over the period of time, a lot of the material was invented. And then currently, if you can see the cathode material which are used in the electric vehicle or NMC or NCA and LiFePO4. Similarly, silicon and tin based on anode also it has come up. So considering their the invention, they were awarded Nobel Prize in the year 2019 in that chemistry field. Next few slides, I would like to discuss about what is the operating principles of lithium-ion battery. As I mentioned earlier, so lithium-ion battery having 4 components. One is the cathode material, usually lithium-based compound. Another one is the graphite anode material. And then in between, there is a separator to avoid the short circuit between cathode and then anode, and then electrolyte. During charging, what happens? Whatever that the lithium which is there in the cathode materials, it gets oxidized and it diffuses through the separator and intercalate into the graphite anode. Whatever the electron generated due to that oxidation, it goes to the external circuit and charging our device. This is the simple principles of the charging of lithium-ion battery. Suppose you may ask how I have to make that fast charging. As you know that, as you have seen that, there is 2 kind of kinetics you have to play with. One is lithium-ion, it is diffused from cathode to anode. Similarly, whatever the electron generated within the particle, it is diffuses within the particle and it is going to the external circuit. If you can play with that, the ionic conduction as well as electronic conduction, if you can make it the faster kinetics, your fast charging also it is possible in the any devices. Lot of research is going on how to make that fast charging by controlling that particle size as well as kind of carbon coating on this the electrode active material. What happens during discharging? This slide shows that how that discharging happens. Whatever the lithium which is intercalated into the graphite, so it is de-intercalate from that graphite and again it is going back to that cathode material. Whatever the electron, it has come from this the anode material, it is powering our devices. Simply saying is that during charging and then discharging, lithium ions settle between the cathode and the anode. If you could be able to control the particle size and the carbon coating, you can make it fast charging and all. And as you know that the lithium-ion battery extensively used in the various applications. So the communication, computer, consumer, extensively we are using that. And then we started using in the light vehicle and then electric vehicle, starting from the 2-wheeler to 4-wheeler. Now they have extended the usage of this lithium-ion battery. In this slide, I would like to give that how that electric vehicle works. So in that electric vehicle, there are 4 important components are there. So one is that the motor, second one is the battery, third one is the power electronics, and then fourth one is whatever the other power electronic devices involved in the operation of electric vehicles. When we talk about the advantage of electric vehicle, so there is statistics. 59 to 60% of electrical energy which is stored in the battery, it can be used for that operation of electric vehicle, whereas only 17 to 21% of energy stored in that the fuel, petrol, diesel, it can be used for the operation. So it is kind of energy efficient. and then it is environmental friendly. This is very important. So there is no CO2 or NOx and other harmful emission is not happening when we are using that electric vehicle. And it is very smooth to operate. And then you can use that your own the domestic electric sources can be used for that charging. And then when we are talking about that advantages, there are several challenges which needs to be addressed for the successful commercialization of this lithium-ion battery, at least for electric vehicle application. The driving range. Driving range, currently whatever the electric vehicle used in India, maximum it can go up to 350 kilometers. But in the case of when you are filling full tank, you can go up to some 400 or 500 kilometers. So that is the advantage of the fuel-based vehicle. But already Tesla and all, they have introduced that the electric vehicle which can go up to 600, 650 kilometers in a single charge. And then recharge time. That is the major the challenges in that electric vehicle. Minimum you need that 3 to 5 hour charging. It is required. Fast charging option is there. Every time you cannot use that fast charging option. When you are continuously doing the fast charging, the lifetime of battery, it will come down. And then battery cost. Nearly half of the cost it goes for the battery. So if we have kind of indigenous technology, that battery cost we can reduce, and then that it will reflect in that the final cost of that vehicle. And then safety issue. Nowadays, you are hearing a lot of accident happening when we are using that two-wheeler. And then I'll be discussing in detail in the later slides. And then this slide shows that what are all the various electric vehicle introduced by that leading automobile companies in that the world market. There are all the companies starting from that Nissan, Tesla, BMW, GM, Skoda, Ford, Honda, all leading company, they have been working on that electric vehicle. Among these, Tesla is the #1 company. They have introduced various the electric vehicle, and then which can go up to that 650 kilometer with the maximum speed of 200 kilometer per hour. Because compared to all that the electric vehicle, so the Tesla electric vehicle having the high capacity battery, that is the reason they could be able to give the driving range of nearly 650 kilometers. Coming into that Indian scenario, so there are companies who introduced that electric four-wheelers. Mahindra, they have introduced that electric vehicle long back, so which can go about 140 kilometers. Recently, Tata Nexon, Tata Tigor, MG Hector, Honda, Hyundai Honda, they have introduced that electric vehicle, which maximum that the Honda electric vehicle, it can go about 450 kilometers. Other Tata Nexon and MG, it can go about more than 300 kilometers. So lithium-ion battery also used in the hybrid car where it can used for that start-stop application. And then when there is a flat road, so that usually in the hybrid car, it is equipped with both IC engine as well as that battery. Whenever there is a high power requirement, you can use that, you can switch over to the fuel mode. Whenever there is a flat road comes, you can switch over to the battery because you don't need that much energy. So that by keeping this battery, you can, so the fuel consumption, you can make it very efficient. You can reduce the fuel consumption by integrating that battery into that electric vehicle. So other biggest market in India for electric vehicle is two-wheeler. There are many companies starting from Ather Energy, Ampere, QEV, Ola, Okinawa, Hero Electric. A lot of this company, they have introduced that the electric vehicle, which can go up to 160 to 180 kilometer in a single charge. And then the capacity of the battery, if you can see about nearly 4 kilowatt hour battery they are using. And then buses also introduced by that the Ashok Leyland. And then recent news, if you can see that yesterday, the Delhi government, they have introduced nearly 150 electric buses for that public transportation. And then they have said that for the first 3 days, they are not going to charge. So compared to other state, in the Delhi, the pollution problem is the biggest issue. And then electric vehicle is the only option to address that issues. And as I mentioned earlier, there are a lot of benefits of the electric vehicle, and then lower fuel cost, lower operating cost, and then there is no CO2 emission and all. And here I would like to say that this is a very interesting cost comparison between the fuel-based vehicle and then the electric vehicle. The Forbes India, they have given that very interesting statistics. Considering average person drives 10,000 kilometers per year. When you are buying the electric vehicle, the cost is about 8 lakhs. As I mentioned earlier, nearly half of the cost it goes for the battery. But when you are calculating the running cost for driving 10,000 kilometers per year, so you have to spend only 5,000 rupees per year, because when you are charging, you have to spend for each charging, you have to spend for about 50 rupees. And then with that single charge, average, if you consider if you are driving in that traffic region, minimum it can go 100 kilometers. For driving 10,000 kilometers, you have to spend only 5,000 rupees per year. On the other hand, if you can see the fuel-based vehicle, even though the cost of the fuel vehicle is less, and then when you are calculating the running cost, there is a huge difference. Considering the mileage of fuel-based vehicle within the city, normally it comes to 10 kilometers per liter. Considering the current price of petrol, rupees 150 per liter, and then considering that mileage 10 kilometers per liter, nearly you have to spend 1,10,000 to 10,000 rupees to drive 10,000 kilometers. Whereas you are spending only 5,000 rupees for driving 10,000 kilometers when you are driving that electric vehicle. This is the huge difference when you are calculating the running cost. And the other most advantage is there is no CO2 emission. So it is kind of eco-friendly. And we can list out, there are so many advantages. When you are buying that electric vehicle through some loan, there is a tax exemption up to 1.5 lakhs is allowed. And then the GST is only 5% for that electric vehicle, against 12% on the fuel-based vehicle. And some state, they are giving the waiver for that registration fee as well as road tax. So these are all the various benefit when you are buying that electric vehicles. And the government, they form kind of a national electric mobility mission for that smooth transition of IC vehicle to that electric vehicle. And then there is the ambitious plan to deploy 6 to 7 million electric vehicle by 2020. Already we are in 2022. It is kind of ambitious plan, but government still trying hard for the transition of IC to that electric vehicle. So in order to encourage the customer, they are giving that a lot of subsidy. So for a two-wheeler, they are giving subsidy of nearly 20,000. For three-wheeler, subsidy of 50,000 is allowed. And then four-wheeler, when you are buying that electric car, 1,50,000 subsidy you will get that under FAME scheme. And then when you are buying that the hybrid vehicle, you will be getting up to 13,000. And then buses, it involves that maximum subsidy of about 50 lakhs. This is what the government, they are trying to attract the customer, and then trying to get that smooth transition of IC to that electric vehicle. By doing this, what is the advantage? So when you are converting that the IC to electric vehicle, you can save up to $300 billion. Equivalent to Indian rupees about 20 lakh crore. We can save the money which we are spending for the importing oils. And then another important thing is we can prevent that the release of 1 gigaton of CO2, which we are releasing to the environment by 2030. These are all that the advantage of electric vehicle. So now I would like to present that the lithium-ion battery research activities which we are doing at ARCI. This slide I would like to give that to young students so that they will come to know what kind of technology, what kind of requirement it is there. So all that technology, basic R&D we have to do. All the Indian institute, starting from that IIT, NIT, all we are good in that laboratory research. we produce that the very good material with good performance, which is showing better performance than the commercially available material. It is not about only the basic R&D. So if you want to take your basic R&D into technology, there is a valley you got to, there are a lot of challenges and then hurdles are there. Once you develop the basic material or process, you have to do kind of upscaling and then prototype fabrication and then demonstration. So a lot of things, a lot of challenges. You have to cross this valley to transform your basic R&D into technology or product. For that, it is not only science is not sufficient. You should have the expertise of engineering as well as management. Management, they will promote our technology. So all kind of multidisciplinary expertise, it is required to take the basic R&D into the technology as well as the product. So in ARC, we have kind of multidisciplinary expertise. And then with this expertise, we could be able to transfer nearly 24 technology to the private industries. So coming into that lithium-ion battery program, we have two major objectives. One is to set up that state-of-the-art pilot scale facility for the fabrication of lithium-ion battery. So this facility we have set up at ARC Chennai. And in ARC Hyderabad, we mainly concentrate on the development of indigenous lithium-ion battery cathode and then anode materials. So this is the overall view of our lithium-ion pilot plant, which is exist at our ARC Chennai. Starting from the material to device, we have that complete facility. And as I mentioned earlier, lithium-ion material is very sensitive to the moisture, and you should have kind of dry room with the different humidity, 30% and 0.5% RH room for the cell fabrication. We could be able to establish all this facility, and these are all that the lithium-ion devices with the different form factor we have fabricated using our facility. So all these cell, initially we have used the commercial material. After some time, there is a restriction for that importing of lithium-ion battery material from that the foreign countries, and then there may be a hike in the prices and all. Realizing that the importance of developing indigenous technology, so in ARC Hyderabad, we mainly work on the development of indigenous cathode and then anode material by scalable process. And so we know that we have to work on that the indigenous development. There are various components involved in that the battery, starting from that cathode, anode, separator, and other the components. If you can see the pie chart, so nearly 32% of cost coming from that cathode material. So if you really want to reduce the cost of the lithium-ion cells or battery, if you can develop that cost-effective cathode material, you can bring down that overall cost of that lithium-ion cells. That's what ARC has been working on, that development of low-cost and large-scale process for developing that LiFePO4 as cathode and then anode material. So recently, you might be seeing that there are a lot of accidents that keep happening for that electric vehicles. So there are a lot of news that has come up. So the main reason, so I will here, so the government have observed all the things, and then the electric vehicle from Pure EV, Okinawa and Ola, recently they catches fire. And then government asked all these companies to recall their the electric vehicles. So as I mentioned earlier, there are three major components in that batteries are battery, motor, power electronics, are the critical components of lithium-ion battery. This slide I would like to show that how it is happening, that the fire accident in that the two-wheeler scooters and or electric vehicles. As I told you already, so the there is three important components: motor, and then the battery, and then the power electronics. The power electronics plays a very critical role between the charger and the lithium-ion battery. So when you are passing the current to the devices, the power electronic monitor the flow of current. So once it is completely charged, the power electronic cut the flow of current into the device. If you don't have that, the quality power electronics, it will not stop the current flow into the devices. If the current is continuously flow into the devices, there is a heat generated within the device. When there is a heat generated, initially it is up to some 69 degrees centigrade. And then slowly the heat, it increases within the device and it damages that the separator usually 20 micron thickness, that the material, it damages. Immediately there is a short circuit between the cathode and the anode, it is happening. And then so all this reaction is or exothermic reaction. When there is a exothermic reaction, there is continuously the heat, it is increasing within the devices. And then after some time, whatever the oxygen in your cathode material also, it has come out of the structure and then it assists the fire within the devices. Once that the heat goes beyond that 200 degrees centigrade and all, there is kind of explosion with the fire, it is happening. So when you are selecting the chemistry, suitable chemistry, the cathode and then anode chemistry is important to avoid this all fire accident. And then a lot of being a member of BAS, we had several meetings with the ministry, and then we have keep working on that. What kind of cathode anode chemistry is suitable for our Indian trophical condition? And then there are other group working on that power electronics, how we can make that the quality power electronic which is suitable for our Indian EV electric vehicle and all. There are a lot of news about all this incident and all. As I mentioned earlier, the chemistry is very important, which chemistry we are selecting. So there are two chemistries, the cathode chemistry is involved in that the lithium-ion battery, LFP, as well as NMC. Each one, it is having its own disadvantage. The main thing is we should not compromise the safety, because whenever the material is not thermally stable, all that temperature it is generating within the battery and it leads to the accident. Because that NMC, it is not thermally stable. It can stable up to 30 degrees centigrade, whereas LiFePO4, it is stable up to 60 degrees centigrade. It is having that superior chemical as well as thermal stability. And then cost-wise also, it is cheaper. Only the issue is the voltage and then energy density is lesser than NMC. So it is fine. So with this, the energy density, I can go up to 100 kilometers, but I can make sure that my electric vehicle is 100% safety. So that's what we feel that LFP chemistry is suitable for our Indian condition. And these are all that the comparison, what are all that the temperature and then what are all the gases it generated when we are using LFP based or NMC cells in that lithium-ion battery. So LFP cell is the 100%, you can assure the safety. Only you have to compromise some driving range and then the energy density. So when you are talking about LiFePO4, it is having kind of olivine structure, and then it is having the capacity of 170 milliampere hour per gram. And only limitation, it is having low electronic and ionic conductivity. When I explained that the basic principles of lithium-ion battery, I was telling that when you are preparing nano-sized particle as well as with a good conductive medium, you can address these two limitations, low electronic ionic conductivity. That is the reason we have been working on that development of carbon-coated nano-sized LiFePO4 particle. So initially we have involved in the two-step process. First, we synthesize LiFePO4 particle using the pilot plant facility. Later, we do that carbon coating on top of this LiFePO4 particle. It is kind of two-step process involved. When we see the performance, our performance, so any material, when you are checking the performance, electrochemical performance, you have to see that how much current it can deliver, how much ampere hour it can deliver per gram of material. If you can see ARC material, it can deliver about 141 milliampere per gram, which is close to the commercial material and better than the other commercial material. So even though material performance, everything is good, but the process involved two-step process. And then later stage, we involve in the development of single-step process, both the nano-sized particle as well as carbon coating. In a single-step process, we could be able to do that. And when you are doing developing single-step process, you can minimize the production cost of that LiFePO4 material. So a lot of advantage when you are working with a single step process, in situ carbon coating. So, and we have used the solid state process. There is no chemical method involved. There is no solvent involved in that. So without solvent, you can minimize the production cost. So these are all the advantages of process developed by ARCI. We have filed a patent for this process. And these are all the physicochemical characteristics of our the ARCI developed LiFePO4 material. You can see that very fine 50 to 100 nanometer size particle we could able to synthesize. And then here, all the particle embedded into the carbon network and other characteristics like XRD. Raman confirmed that the pure phase we obtained. And then the carbon thickness, if you can see, nearly 5 nanometer carbon is coated on LiFePO4 particle. As I was mentioning that it is not only about that lab scale R&D. You have to do kind of upscaling of the process, whatever you developed at the lab scale. And then we could successfully upscale our process to produce 10 kg per batch. So that material with the help of one industry, powder metallurgy industry, we have used their facility. And then we have successfully demonstrated our process for that large scale demonstration also. This material we have tested and then benchmark with the commercial material. And then this is our ARCI LFP material performance. If you can see the performance, it can deliver 139 milliampere per gram. And if you can see the other two commercial material, the performance is almost close to the ARCI material. But when you go for that 5C, so it is, we call this is current rating. 1C means you are giving charging 1 hour, discharging 1 hour, all it happens. When you go for fast charging, it is 5C. Nearly you are giving only 12 minutes for charging, 12 minutes for discharging. At that fast charging, our ARCI material could be able to deliver the capacity of 110 milliampere hour per gram, whereas the commercial material, it can able to deliver less capacity compared to ARCI material. So we have developed process and we have demonstrated for producing large quantity of material. Then we have fabricated that lithium-ion cells using our indigenous material. And we have compared the performance of our indigenous cells with the cells made from that commercial LFP material. And if you can see the performance of the both cells, the cell made from that indigenous ARCI LFP material, it can able to give the capacity of 92% even at the higher C rate. Whereas the cell made from the commercial material, it can able to deliver only 77% of the initial capacity. And then the cycle life also, it can able to deliver more than 85% after 250 cycles and all. These are all that the highlights and then salient features of our ARCI developed material. Once we develop that technology, we have transferred to that the private industry. In the last year, August, we have transferred the technology. So I am proud to say that we are the first institute to develop and demonstrate that LFP technology, which can be used for the lithium-ion battery. And we are the first one to transfer this technology to the private industry. It is not only transfer the technology, we have demonstrated that the technology to the technology receiver, and all the technology transfer as well as demonstration has completed. Now the company, they are trying to set up the big plant. So with the capacity of 1 ton per day, they are trying to establish, and another 15 months, so that the plant, it will come for that the production line. This is what about that the cathode material. Anode material, we have been using that lithium titanate. So in the conventional lithium-ion cell, they have been using that graphite as an anode material. Why we are using lithium titanate as an anode material? So again, safety-wise, it is important. And then there are some structural changes occur when you are using graphite. Here, there is no structural changes occur during charging and recharging. It is kind of zero strain material. And within 6 minutes, the lithium titanate cell can be charged. So for that kind of high power application, this LTO can be used. And we have been working on that development of this lithium titanate by solid state process. we are using that high energy milling unit with the capacity of 2 kg per batch. Initially, we started working on that. And when you see the performance, so we are getting the performance of about 164 milliampere hour per gram ARCA developed LTO, whereas commercially available LTO, it is showing about 167 milliampere hour per gram. And then important thing, if you can see that the cost of ARCA developed LTO, it is only 1200 per kg, whereas the commercially available LTO cost is 5000 per kg. Our the unique process plays an important role to decide the cost of that, the production cost of the LTO material. Like LFE, here also we have done that large scale demonstration for the production of LTO material in collaboration with the industry. And then, so we are using about 15 to 20 kg per batch milling and all. So the demonstration is going for this LTO material. And so here I would like to say that I was saying that it can be used for the high power application. So initially I mentioned that you can charge your devices at a different C rate and all, starting from that 1C. 1C means you are allowing the device to charge within 1 hour. 30C means you are allowing your charge only for 2 minutes. When you are using this lithium titanate as an anode material, you can charge your device within 2 minutes, which can deliver the capacity of 84 milliampere hour per gram. So that is the advantage of this lithium titanate cells. And then we have that qualified our process using that different lithium raw material. As you know that lithium raw material, it is available only South American country and then China. So we obtained that lithium source from different sources, and we found that our process is suitable for all kinds of lithium raw material. But the important thing is when you are using raw material from this BARC and Toyota, the cost is only 1500. Whereas when you are buying from that SRL, the cost is about 11,410. By using these lithium sources, you can bring down the production cost nearly 2,500 rupees per kg. So like LFP, we also fabricated that lithium-ion cell using our indigenous LTO material, and we obtained that the capacity of 80% capacity retention after 1000 cycles, and with a different cathode combination, we have prepared cells. So now we are in the process of technology transfer of this LTO anode material to industries. And our the research on LTO is highlighted in the social media, and it was telecast in that Rajya Sabha TV. If time permits, I will show that video also. So another 10 minutes, I will wind up. So please allow me to present for another 10 minutes. So far I am talking about the development of lithium-ion battery materials. So all that the battery involves lithium-based compounds. Suppose if you are exhaust with the lithium-ion, there is no more lithium available in that. You have to parallelly work on that other energy storage device, which is free from lithium-ion battery. Supercapacitor is the one device where both cathode and then anode is only carbon-based material used as the electrode. There is no lithium involved in that because lithium is available only Argentina, Bolivia, Chile, and then China. If you exhaust with the lithium, you have to work on that different storage devices, and then supercapacitor is one of the devices. As I mentioned in my introduction slides, so here in the supercapacitor, there is no the oxidation reduction reaction it is happening. It is kind of only the absorption of electrolyte on the surface of cathode and then anode, it is taking place, and it forms kind of electrochemical double layer capacitors. So the capacity directly related to that, how much the surface area of cathode and then anode material, how minimum the thickness of the electrochemical double layer capacitor. The unique advantage of supercapacitor is there is no lithium involved in that. Within a minute, you can charge your devices, and then the cycle life, it is enormous. Nearly 10 lakh cycle you can use this device without any further structural changes or any damages. Considering this advantage of fast charging, already China, they have implemented this supercapacitor technology for the public transportation. Within the city, every 10 kilometers, they have put up the charging station. the bus which is equipped with the supercapacitor travel 10 kilometer, and then it stops at the bus stop. By the time passenger get in, get out, so the supercapacitor model get charges, and it run for another 10 kilometer without any issue. So this is what the advantage of supercapacitors. And in many countries, they have implemented supercapacitor powered buses for public transportation. What we are doing at ERCA, so we are trying to work on the development of material for supercapacitor devices. And using our material, we want to fabricate the indigenous device, and then we want to demonstrate. We have taken up 3 activities. One is material development. Second one is fabrication of indigenous device. Third one is demonstration of this electric vehicle for that real applications. So in the commercial Maxwell device, they are using coconut shell derived carbon as a carbon source for making supercapacitor grade carbon material. So you may ask, in India, we have plenty of coconut shell. Why don't you use that coconut shell as a carbon source? There is a report which says that the Indian coconut shell is not suitable for making supercapacitor grade carbon material because it is having lot of ash content, lot of minerals are there, sodium, potassium, all minerals are there. So when you are converting this carbon source into final carbon, so the high temperature heat treatment involved in that, all the minerals are converted into respective metal oxide. It is giving too much the resistance during charging and discharging process. That's why our coconut shell is not suitable for making the supercapacitor grade carbon material. We tried several bio as well as industrial waste. Initially, we started with the jute stick. So you know that jute plant. So there is a fiber which is having some commercial value. They are using for making that jute bag and other product. After extracting jute fiber, you have that kind of jute stick, which they are dumping as a solid waste. What we have done, we have taken that jute stick as a carbon source and we have made it a fine powder. And by adding KOH, it is kind of the activation reagent we have added with that jute stick. And we have converted into that kind of graphene-like structured carbon, where Raman and as well as ACM analysis confirm that the graphene-like structure is formed at the end of the process. And when we are validating the performance for the supercapacitor performance, so our material able to give that 132 farad per gram, whereas commercial material, it can able to deliver only 91 farad per gram. And then you can see that the capacity is so stable for 10,000 cycle. Mainly, we have played with the surface area, structure, and then pore structure, everything. So we have fine-tuned and then different temperature, how the graphene-like structure is changes when you are increasing that the heating temperature and all. So many optimization we have done. And then finally, we could be able to synthesize graphene-like structured carbon from that the bio waste, which is dumped as a solid waste. And this work we have filed a patent, and recently that patent also it was granted, and we have published this work in the couple of good journal. Even though we achieved good performance, but the issue is we are getting only 35% yield. When you are start with that 1 kg of jute stick, finally your carbon is only 350 grams. So commercially it will not be attractive. So you have to select the carbon source which is having the high carbon content. In collaboration with the HPCL, we have initiated one project, and you know that petroleum coke, which is generated in huge waste from the oil industry. The important advantage is this petroleum coke having the high carbon content, and then it is cheap. It is also abundant. We have used the similar process to convert the petroleum coke into the porous carbon material. Like jute stick, we could be able to synthesize the graphene-like structured carbon, and the performance, if you can see that 128 farad per gram for the pet coke derived carbon, which is high compared to the commercially available carbon, which is about 98 farad per gram. And the most important thing here is we could able to achieve that yield of nearly 60 to 70% yield. So the material showing high performance, high yield, and then whatever the raw material which is available in abundant with the cheaper cost. So these are all the advantages of the pet coke derived carbon for supercapacitor application. This work also we have filed a patent. And then, so we have successfully synthesized the material from that bio as well as industrial waste. Our final target is we want to demonstrate this supercapacitor for real application. Before going for indigenous device, we have fabricated the model using the commercial Maxwell supercapacitor and assembled a model and integrated into the bicycle and demonstrated that supercapacitor power bicycle for that driving range of 2 kilometers. And then this whole model you could be able to charge within 1 or 2 minutes. So next our intention is we want to fabricate our own device using our own material. For that, we have set up the facility for the fabrication of supercapacitor device. There are nearly 11 equipment involved for the fabrication of device. And we have set up all this facility. And using carbon material, we have made carbon cathode as well as anode. And then in between, we have kept the separator. And then we have made kind of the jelly roll, which is having cathode, anode, and then electrode. And then later, we have done so many processes called flattening and then laser welding. And then after laser welding, we have kept this laser welded jelly roll into the can. And then finally, we made this the supercapacitor device. So all starting from the material to all the process, it is kind of indigenous effort involved for making the final supercapacitor device. So far, we have made so nearly more than 50 supercapacitor devices we have made. Like material, we always benchmark with that the commercially available Maxwell device. So if you can see the performance of our devices and then that commercially available Maxwell device. ARC device is able to deliver the capacity of 1198 farad, whereas the commercial Maxwell device, it can deliver only 1165 farad. In terms of energy, ours is higher, 5 whatever kg it can able to deliver, whereas commercial is only 4.5. And volumetric energy density is slightly lesser because that our height of the cell is slightly higher. In all aspect, in terms of capacity, in terms of energy density, our devices is showing that superior performance compared to the commercial Maxwell device. So our final target is we want to demonstrate for electric vehicle application our indigenous device, like what we did in the commercial Maxwell model. We have assembled indigenous device in a model, and also we worked on that the power electronics, which can able to monitor that voltage and then current, and then we have equipped in that bicycle, and then we have drive that the bicycle with our indigenous supercapacitor model for the driving range of 1 kilometer, where we can charge that supercapacitor model within 2 or 3 minutes. This is the successful story for that the supercapacitor device. And then now we are trying to extend this supercapacitor for that hybrid application. As you know that lead acid battery, it cannot deliver that high power, and the cycle life also it comes less. So in order to increase that the power performance, or in order to increase the lifetime of lead acid battery, we are trying to integrate supercapacitor into that lead acid battery. And then whenever there is a power electronics between the lead acid battery and the supercapacitor, so when there is a ramping or when there is a speed breaker, you need that high power. As it is lead acid battery, it cannot be able to deliver that high power. So whenever there is a requirement, it will be switch over to the supercapacitor. So that it will deliver the power. When the normal road comes, so the power it comes from the lead acid battery. By doing this, we can increase the performance of the lead acid battery in terms of power capability as well as cycle life. This is what already we have been doing. So this is that lead acid battery, and then we have put our supercapacitor model, and then a lot of data acquisition, data analysis going on. And again, social media, they have highlighted our the supercapacitor research also, and various article, and then the news, they have covered our supercapacitor research activities. And with the time constraint, I'm not going into this one. So what is the take-home message from this presentation? So what we understood is lithium-ion battery technology is essential to reduce the carbon footprint and the global warming. Whatever the developed process at ARCI for the development of cathode and then anode material using that pilot plant facility has been successfully accomplished, as well as it is demonstrated in device level. And ARCI developed a cathode and then anode material exhibit excellent electrochemical performance, which is at par with the commercial material. In the supercapacitor program, we successfully fabricated supercapacitor device using that indigenous developed carbon material, and then capacitor shows that high capacitance. And this is the capacitor first time with that 1200 farad capacitors, first time we have made in India, and then successfully demonstrated for the real application. This is the acknowledgement. I would like to thank my director, Dr. T.N. Rao, who is heading this the energy storage device division in ARCI, and also thank Dr. Gopalan and our previous director for their kind support and encouragement. And I also thank all my colleagues, and I extremely thankful to all my students who did all their work with dedicated and passion. They have shown for that successful deliverable of all these projects. And this slide I would like to show to all that student, which will be beneficial for them. ARCI giving opportunity for that young students who are doing the final year, the MSc, they can come to ARCI and then they can do their project work. So we are giving opportunity starting from 3 months to 1 year. And once you completed that master's, you can join as a graduate trainee, where ARCI giving opportunity to work for 1 year with a kind of stipend. So meritorious student, they can apply, and then they have the opportunity to work on that all that technology oriented project. In addition to that, we are giving also advertisement for JRF and SRF. So once they select JRF and SRF, they will be registering at some IITs and then NITs. We are having ARCI having some kind of MOE with them, so that our students get PhD registration there. But most of their research work they will be doing at the ARCI. In addition to that, we may call sometime for scientists with a different level, junior, senior, and middle level. Depends on that project what we are having. And also those who completed a PhD also they can apply for this post. And then for further detail, you can refer our website www.arc.res.in. And interested student who are doing the final year, and then who wants to do their project work at ARC, they can send their CV to hrd@arc.res.in. Finally, let me thank again that the organizer for giving me opportunity to present our work in this international conference. I thank Professor Sigabuddin sir, Professor Jafar, Professor Feriyasamy, and other organizing committee members for this opportunity. I wish young students to work hard and come up in the life with the flying colors. Thank you all. Thank you for your patience. And then I'm open to any question. Thank you all. So may I run 1 or 2 videos? Is it okay? This video is about ARCI.
Welcome to an ever-evolving research and development center that has been consistently intensifying efforts in translating research to technology. ARCI, International Advanced Research Center for Powder Metallurgy and New Materials. An innovative center that has been working to quench India's thirst for high-performance materials and processes for niche markets since 1996. ARCI, an autonomous R&D center of the Department of Science and Technology, DST, Government of India. ARCI is primarily focused on developing nationally unique technologies through its application-oriented research and transferring them to Indian industry for commercialization. ARCI has been continuously evolving the formats by which it may engage with stakeholders from other R&D labs, academic institutions, and industrial organizations to develop technologies and innovative solutions suited for the changing world. ARCI presently has 11 centers of excellence. Its COEs have consistently worked towards development of new materials and processes, providing solutions to industrial users and transfer of technology for commercialization, including the PEN fuel cell system for stationary and mobile applications, oxide dispersion strengthened ODSTs for high temperature applications, nano composite functional coatings for efficient solar thermal systems, joining technologies for automotive light weighting, coating technologies for power plants, ultra-fast laser microprocessing to create features in the sub-micron sizes, high-performance ceramic components for applications ranging from energy-efficient air heaters to SiC-based substrates for optical applications. True to its mantra, translating research to technology, ARCI has successfully transferred 16 technologies to 28 receivers and more than 150 technological applications for industrial and strategic use. Detonation spray coating technology in late 1990s for aerospace, textile and hydropower sectors, which is still continuing to evolve with advanced features.
My experience is very unique with that Capacitor center. Though I started with detonation spray coating for technologies like micro-oxidation, electrospark coating, and recurrent in Indian market.
Anti-mine boots for security personnel. Nanomaterials for textiles finishes with antibacterial and self-cleaning ability when exposed to sunlight.
ARCI is a friendly, collaborative, and a competent materials partner. ARCI helped us to take this idea from mind to market. Silver technology was indigenously developed and patented worldwide. This helped in improving social wellness and hygiene. We received 2 national awards, one from TDP, another one from Nano India. We thank and appreciate ARCI for their contribution for this global project.
Silica aerogels based flexible sheets with outstanding properties for industrial thermal insulation. Apart from these, ARCI continues to strengthen its patent portfolio with filing of more than 100 national and international patent applications. ARCI serves as a springboard for inculcating interest in the young minds to opt for research as their career. There are innovative approaches afoot in the areas of materials for energy and environment through cost-effective solar cells, storage batteries, and supercapacitors for electric vehicles, low-cost fuel cells, magnetic materials, thermoelectric devices to recover waste energy from exhaust, nano composite coatings to replace chrome-based coatings, advanced manufacturing processes such as additive manufacturing, laser micromachining, high-energy milling, high-performance ceramics, new steels for use in fusion reactor and supercritical thermal power plants, and improved machining tools.
ARCI 20 is now very enthusiastically poised. We would like to elevate the research enterprise at ARCI by further intensifying our interactions with the industries and user organizations, other R&D institutions, and together synergistically convert our knowledge into technology which is commercializable and usable. We have also resolved to align ourselves with the national missions like Make in India. The strengths and capabilities that we have built over the years, we are sure and confident that we'll be able to aptly respond to any materials technology related needs of the country and the industry, and that is a promise from Team ARCI.
essence, ARCI is evolving and innovating continuously to contribute to the field of application of materials and manufacturing technologies in general.
Sir, one more 2-minute video is there. With this, I will finish.
Hyderabad-based ARCI, an autonomous institute under the Department of Science and Technology, is continuously working on different materials to develop high-quality lithium-ion batteries and to reduce the dependency on imported products. To realize this goal, the researchers of the institute have now developed an indigenous technology to synthesize a lithium titanium oxide anode for fast-charging lithium-ion batteries used in electric vehicles. Take a look.
Fast-charging lithium-ion batteries are in high demand for portable electronic devices and electric vehicles. However, import of lithium titanium oxide, an anode material for high-power LIB application, makes the batteries costly. Plus, the complicated process of synthesizing this chemical makes things more difficult. Now, researchers working at the Center for Nanomaterials of ARCI Hyderabad, an autonomous institute under the Department of Science and Technology, have developed a simpler method to produce LTO, which can make the lithium-ion batteries less costly. Indigenous developed from abroad to lithium titanium oxide has emerged as a superior anode material for high-power lithium-ion batteries due to its thermal stability, excellent life cycle, and safety. Using titanium dioxide and lithium carbonate as precursors, ARCI team has developed a simple, economical, scalable, and energy-efficient technique for the production of LTO anode with improved electronic conductivity. LTO anodes exhibit recharge efficiency exceeding 98% compared to the other carbon-based anodes and have a life cycle of 20,000 cycles. These can endure temperatures ranging from -30 degrees to 55 degrees centigrade, making them highly suitable for difficult weather conditions in India. The high-energy milling method developed by ARCI makes them more economical.
ARCI has imported technology for production of lithium titanate and anode material for fast-charging lithium-ion battery for tropical Indian climate. The technology has been successfully developed at ARCI and validated at the device level. Further, the technology has been patented both in India and abroad. With this development, we are able to offer an indigenous, cost-effective technology for production of high-performance anode material for lithium-ion batteries, which also has long cyclic stability.
Although the use of electric transport is being promoted to save the environment from pollution, yet there is a dearth of economically viable electric vehicles. The cost of such vehicles increases with high power and high performance batteries. The zeal of ARCI scientists to develop indigenous technologies for high capacity, fast charging, and long-lasting batteries will definitely make electric vehicles economical in the future.
Thank you, Professor Peresami. I am done. Sorry for taking long time. Yeah.
First, I thank the opportunity given me to propose the vote of thanks. I am very glad to be standing here to express my vote of thanks. Really, staff invited is very much helpful to the young researcher. It is a social relevance project. Today, need is more because every day the petrol and diesel prices are increasing, and also go green environment is essential. So in this aspect, really once again I thank the today resource person, Sir Dr. Srinivasan Anandan sir. Sir, already I pointed out, sir is the illustrious alumnus of our
popularity for military aerospace application because it's longer life and we have better air capability. And thus, we also insisted the rate comparison of petrol vehicle and the electric vehicle. Then, sir, we detail about the super capacitor. So all of you very familiar with the super capacitor. Super capacitor is a storage device and a energy storage. It stores the electrical energy through the electrolyte by the forming of AA capacitors by the charge separation on the interface between the electrolyte and a bad solution. That's how he insisted about the development of indigenous supercapacitor, synthesis of porous carbon materials from jute stick. And finally, sir detailed about the fabrication for a supercapacitor, then hybridization of a lithium battery with a because in a motor vehicle like car bus we are using lead acid battery. By the hybridization of the supercapacitor, we can get more efficiency. So at this sector, once again, I really thank the today's resource center, among this procedure and accept our invitation and deliver your innovative talk on storage material. So thank you, sir.
Thank you. Thank you so much. Okay, Professor Peresami, I am leaving the meeting. Okay. Thank you. Thank you all.
Thank you, sir. Now it's time for lunch break. Arranged at the chemistry department, personal chemistry department. So all the participants are asked to arrange in the hall at 2 p.m. for technical session 2. Family oral presentation will also be there. Thank you.
Good afternoon, Anil Kumar, sir. Sir, I am audible?
Yes, sir, I can hear you, sir. Good afternoon, sir.
Okay, sir. We will start the program in a couple of minutes.
Yes, sir, no problem.
It's a privilege or honor to embrace afternoon session. The research person that can be Malima is working as a senior associate professor in the Department of Chemistry, Manipal Institute of Technology, Manipal Academy of Higher Education, Manipal. He has more than 20 years of teaching experience in the teaching and CRO industry. Dr. Anil, a teacher, engineering chemistry, as well as UG and PG chemistry school. His area of research is natural product, synthetic chemistry, and chemical mechanics. He has published more than 50 research papers in international reputed journals. He has successfully guided 2 PhD and 3 students. At present, 3 students is pursuing PhD program under his guidance. More than 5 students obtained their PhD degree as a program. Now I invite Dr. L.P. Amit Kumar to deliver a special lecture on the essential modules of pollutant removal. In syllabus area. Thank you, sir.
Thank you, sir, for those nice words. I'd like to thank the organizers for giving me the opportunity. Am I audible?
Yes, sir, audible, sir.
Okay. So can I share the screen?
No, sir. The screen is not shared now, sir.
That's right. Can I do it now, sir? Can I share the screen?
No, sir. Now your screen is visible, sir.
Sir, now visible.
Can I start?
Yes, sir.
Yes, sir.
Okay. Thank you, sir. Good afternoon, one and all. Sir, my video is required, or can I mute my video? Turn off my video. Good afternoon. Good afternoon, all the participants of this international conference. I'd like to thank the organizers for giving me an opportunity to present my small topic on the designer molecules for pollutants removal and in silico studies. I'm working as an associate professor in the Department of Chemistry at Manipal Institute of Technology, Manipal Academy of Higher Education, Manipal. Before I proceed with the contents, we'll have a small video and then we will continue with our presentation. Hope all of you are quite aware of this particular small video. we presume that the donkeys are fit for nothing. And in this case, the first two donkeys that were there could easily go without thinking that the bar can be taken off. But the third donkey was smart enough so that it does the same thing, but it has to go out of that particular place, but without any too much of effort. All it has to do is just reduce that bar or make sure that the bar is on the floor. The point to be noted is all of us does some work, and most of us, we assume that they're all donkey work. And no doubt about that, even I do the same thing sometimes, but we should do it in a smart way, just like the third type that we did. Therefore, whatever the research that we do it, if we can fine tune that with the smartness, then the results are much more encouraging and we can anticipate what we are going to get as a final result. So in this case, the pollutants are the critical ones. And as all of you are aware of that, there are three types of pollutions that one can expect: air, water, soil. And there are pollutants like carbon dioxide, sulfur oxide, oxides of sulfur, oxides of nitrogen, volatile organic contents, asbestos. All these things are the pollutants for the air. Similarly, heavy metals, pesticides, microorganisms, and so on and so forth are the pollutants for water. And the same heavy metals and pesticides are even the pollutants for the soil, apart from any other biological samples that one can think of. So if we can target any of these things, at least one of these things, then majority of the problems are resolved with respect to the environment. And there are different strategies for the removal of pollutants. If I go with the air component, the carbon dioxide, you can think of planting more trees so that the carbon dioxide is taken care of. Or there are different methods of capturing the carbon dioxide. Or there is a new technique known as sequestration, wherein carbon dioxides are sequestered and get converted into different products. Or you can think of carbon dioxide, wherein convert this carbon dioxide to the useful products like phosphates or any other single carbon components, organic molecules. Similarly, for sulfur dioxide, limestone is a classic example wherein it captures sulfur dioxide. Or instead of limestone, one can also think of sodium sulfite. Also, there is another methodology of scrubbing the sulfur from the sulfur dioxide so that the sulfur can be used for any other application. And for volatile contents, again, the classic methodology is activated carbon, or one can convert these volatile contents into oxidizing agents using either hypochlorite or hydrogen peroxide or any other oxidizing agent. Similarly, for asbestos, the gold standard methodology is encapsulation method. Similarly, for water, the removal strategies are for heavy metals. Most of the times it's chemical precipitation method, wherein the sludge is taken out having high content of heavy metals, or the classical chemical method of ion exchange, or the newer technologies wherein they use adsorption or membrane filtration, and reverse osmosis solvent extraction are a little bit expensive to a certain extent, and therefore rarely used techniques are the last two ones. For pesticides, again, the gold standard methodology is chemical precipitation. Invariably, aluminum sulfate is used, or the newer methodologies uses adsorption technique, wherein activated carbon is used. For microorganisms, they just kill the microorganism either by treatment with chlorine or flashing the UV, or they do the ozonation process. Again, for soil, the heavy metals are taken care of by biomass producing crops, wherein the plant absorbs all the heavy metals, or it can be put into a reactor, two types of reactors, batch or slurry reactors. And in that, they use either citric acid or ferric chloride, or it can also be thermal desorption, wherein the heavy metals are taken off from the soil, and that heavy metal is used for different application purposes. For pesticides, Again, the microbial degradation is one of those methodologies from the soil, or the highly expensive one like supercritical extraction, or the thermal desorption, wherein the pesticides are taken off from the soil and that pesticide is treated with various other chemical reagents to neutralize its effect. For biologicals, phytoextraction, wherein the plant takes up all these biological samples, or one more methodology is vermiremediation. The worms takes about all these biological samples, and in the process, the biological sample is taken off from the soil sample. Now, among these three pollutions, let me concentrate on water pollution. And the water pollutant removers, there are different categories. Carbon adsorbents, wherein activated carbons, activated carbon fibers, molecular carbon sieves, fullerenes are used. Or it can be mineral adsorbents like silica gel, activated alumina, metal oxides, metal hydroxides, zeolites. When I mean zeolites, the clay minerals or pillared clays or inorganic nanomaterials are used, which removes water pollution. Or the other adsorbents like synthetic polymers, composite adsorbents, mixed adsorbents are used. This is one way of classification of the pollutant removers. There is one more methodology of classification. When I mean activated carbons, even the wood, peat, coconut shell, coal, any of those grades of coals. Or it can be inorganic, same thing as we have discussed in the previous slide, activated alumina, silica gel, zeolites, molecular sieves, or resins, invariably ion exchange resins, wherein polymeric organic resins, non-porous resins, porous cross-linked polymers, any of these polymeric materials are used. With respect to the mechanism, these are the four mechanisms that usually operate so that the adsorbents are taken off from the water molecule. Again, if I go back to the previous slide, all these things not necessarily concentrate on the adsorption process. Sometimes it dissolves, sometimes it precipitates, but I'm going to concentrate on the adsorption process. In the adsorption process, the weakest adsorption is the physical adsorption, physisorption. And when I mean physisorption, it can be due to surface adsorption, van der Waals interaction, hydrogen bond, hydrophobic interactions, or little stronger adsorption is with respect to chemisorption, electrostatic interactions, or it can be because of the complexation, chelation, inclusion complex formation, or any other strategies used in chemisorption. And in ion exchange, there also the adsorption takes place, and it's reversible exchange of ions. The one which are bound to the resins are released. Thereby, these pollutants gets adsorbed onto the resinous materials. Or it can be the precipitation, micro precipitation, surface precipitation, proton displacement. These are the different strategies or the mechanisms to take out the adsorbents that are there in water. Now we'll see the design of molecules vis-a-vis synthesis. Now all of us are quite comfortable with synthesizing the molecules because that's our bread and butter. As a chemist, we have to think of what's the new molecule that I can think of to solve a particular problem, whether it is a biological problem, whether it is an environmental problem. All of us keep looking for some molecule, inorganic, organic, polymeric, whatever it is. But here in this particular slide, why we should design a molecule and why not synthesize it straight away. So the advantage of designing is it's safer, it's cheaper. When I mean cheaper, all I require is a computer and I can synthesize any number of molecules that I can design any number of molecules. It's safer because I'm not at all handling any chemical in my hands, or there is no hazard associated with exposure, chemical exposure, toxicity of those chemicals, inhalation problem, all those things are totally avoided because I'm not at all handling any chemical. The advantage of designing is I can test a product before synthesizing it. The meaning of that statement is, if at all I synthesize a molecule A, what property that this molecule is going to exhibit? Those are the things that I can test it while designing the molecule itself. And I can also explore what if questions. What if I increase the pH of this solution? What if I increase the temperature of this, whether the degradation takes place or whether the breakdown takes place, the degradation of the molecule takes place, or what if the concentration, if the pressure is increased, can I convert into liquid form at a suitable temperature and pressure? What's its critical parameters? All those things I can check while designing the molecule. It's not as rosy as one can think of. At the same time, it has got its own disadvantages. Most of the times, the problem comes with the software. And of late, what I can expect, what I have observed is there are lots of open source softwares are available wherein the cost is not that much high. One can easily work around that particular problem, high cost. Time and expertise is the critical thing. It requires little more time to get adjusted with what we are basically looking for. And one has to have an expertise in designing or working out with the software part of it. Like synthesized molecules, wherein I have got a sure result, whether the molecule exhibits this particular property or not. Here in this case, there may be a slight deviation. It may not be that much realistic or reliable as one can think of the synthetic molecules, 100%. But if your chemistry is strong, if your hypothesis is strong, then there is a very high possibility that the last point is also taken care of. At the same time, synthesis got its own advantages. When once you have a molecule in your hand, you can evaluate its property, whether it adsorbs, whether it exhibits this particular biological activity. All those things I can easily do it if I have got a molecule in my hand. Sometimes we expect a product A and we end up with product B. So unexpected products is quite common. And that leads to a new theory or refine the theory what has already been there. And there are lots of classical examples that one can think of while discussing this advantages of synthesis. You expect product A and you end up with product B. Then you go back and check it out why you got this product B. And there are lots of new theories that are being evolved basically because of unexpected product. The advantage is that you are going to create lots of skilled workforce. Whenever any chemical industry is there, basically they all require skilled workforce, and the synthesis is one such skill that these industries will look for. Same thing, even synthesis has got its own disadvantages. The chemicals, you don't know what molecule that you are synthesizing, what are all the raw materials that you require. To give a simple example, I'm looking for a molecule wherein I require just 1 gram of one of those reactant, and the company says that they can sell only 100 grams. Less than that, they are not going to sell it off. So the high cost is there. Even though I require just 1 gram, sometimes I have to buy 100 grams. There is high risk associated with safety aspect. If you're basically working with all those cyanide reactions or those reactions wherein there may be a possibility of fire being generated, or there may be a reaction where oil bath at high temperature. All these things are the safety risks that one has to take care of. And the last one, all of you will agree with that, the yield is highly uncertain. We anticipate that a particular research paper says that the yield is around 92%. Whatever the variations that I do, I may not reach that 92%. Instead, it may be somewhere at around 60 to 70%. So there is a high risk of yield, high uncertainty associated with the yield. I may end up with even 2% of the product. So those are the disadvantages associated with synthesis. And let us assume that I'm going to design a molecule before I synthesize those molecules. Then I have to think of some parameters which gives me what type of parameters that I have to consider before designing the molecules. Then the hit list is almost, I can hit the bull's eye. Therefore, we have to be aware of what are the parameters so that the adsorption is taken care of. The first and the foremost, nature of the adsorbent. And when I mean nature of the adsorbent, it also includes that whether the physisorption takes place or the chemisorption takes place. And again, surface area, you're all aware that the higher the surface area, better the result. Therefore, surface area plays a role. And the nature of the surface also plays a role. If it is a smooth surface, the adsorption is not great. And if it is a rough surface, adsorption is to a greater extent. Nature of the gas, if I am looking for gas adsorption, nature of the gas plays a role, whether I'm adsorbing nitrogen gas or carbon monoxide, carbon dioxide, whatever the gas that I'm looking for. So I should know what is the nature of the gas that is going to adsorb. The exothermic process, adsorption is an exothermic process or endothermic process, and thereby I can decide whether this reaction is feasible or not feasible. Again, as I increase the pressure, there is a very high possibility that the desorption takes place. So till what pressure I can maintain this system? Again, as I increase the temperature, desorption takes place. So there is a critical temperature below which the adsorption is to a greater extent. pH of the medium, concentration of the pollutants or the adsorbents, and whether the contact is for a very short period or it's for a very long period of time. The contact between adsorbent and the adsorbate. Apart from that, there are other parameters that one has to be aware of. Adsorption capacity, adsorption rate constant, adsorption coefficient, adsorption kinetics, adsorption affinity, adsorption energy, and the thermodynamics of adsorption, enthalpy, entropy, all those parameters, and also the solubility of the solute if I'm looking for any solution. So how do you predict these parameters? Let us assume that you're looking for formation of hydrogen bonds and resulting in the adsorption process. Then we have to look for what stabilizes the configuration. If I have got an electron withdrawing group close to hydrogen, whether it stabilizes the configuration or whether should I have more of electron releasing groups, whether should I have any hydrophobic groups to be present, any of those parameters to identify what stabilizes the configuration. Then how can I make sure that the adsorption capacity, when I mean adsorption, adsorption capacity increases with the hydrogen bond formation. So those are the things that one can think of. And if I want to do DFT calculations, I can expect the DFT results will give me the optimized geometry. Most of us were quite comfortable with carbon sp3 hybridization, bond angle is 109.5 degrees. We are quite comfortable with all these numbers, but in reality, the geometry can be entirely different. So the software does all those calculations. It changes all its bond angles, bond lengths, everything it changes and gives you the optimum energy wherein, optimized structure wherein the energy is at the lowest minimum. And they call it as global minimum. And you can find what is the minimum energy of the optimized geometry. Those are the things that one can expect in simple DFT calculations. And also you can do molecular dynamics. And this is little bit time consuming process and requires little bit of high-end computing facility. I cannot just run it on my normal laptop or desktop. I require some amount of graphics card. And in this particular molecular dynamics, let me assume that molecule A adsorbs molecule B. In molecular dynamics, I can have an external parameter. I can vary the temperature, I can vary the pressure, I can vary the concentration. And with respect to time, I can figure it out whether the molecule still binds to that substance or substrate, or it detaches from that. Those are the things which I can study when I do molecular dynamics. So those are the tools that one can think of. And if I'm looking for glycoside enzyme complex, which is also nothing but adsorption process. Now I'm slightly deviating in this particular slide and again come back to the normal water pollution. I'm using all these tools or techniques so that you get what exactly I mean by the parameters. So if a nanoparticle is adsorbed on a substrate, I can easily figure it out whether the nanoparticle is adsorbed in physisorption mode or chemisorption mode, and to what extent the bond is strong or weak. Those are the things that I can calculate. Or I can dock the molecule. When I mean dock the molecule, I'm not necessarily confining myself to the enzyme and the ligand. It can be even an inorganic molecule binding or docking to a metallic surface. The molecular dynamics, as I've discussed in the previous slide, to study the strength of that complex, the adsorption complex. And I can also calculate adsorption energy to study whether the process is stable or unstable. Let me give you an example. The adsorption of flue gases, carbon dioxide, nitrogen, methane, or any of these things, on amorphous solid cucurbituryl. So you have got an organic molecule, cucurbituryl, and on this molecule, these gases are being adsorbed. So what's the binding of carbon dioxide molecule inside the cavity? Whether the cucurbituryl facilitates the carbon dioxide molecule binding, or whether nitrogen is preferred or the methane gas is preferred. So I can easily figure it out which molecule easily fits into that. And I can also do energy decomposition analysis, wherein disperse force for the uptake of carbon dioxide inside the cavity. You have cucurbituryl, if you can remember, or if you can Google it at your convenient time, you can assume, you can just check it out and confirm that it has got a cage-like structure. It has got a cavity inside. And these carbon dioxides are captured inside those cavities or any of those gases, flue gases. So if the uptake of carbon dioxide inside those cavity is strong or weak, that I can check out by studying energy decomposition analysis. I can calculate what is the energy of decomposition when cucurbituryl binds with carbon dioxide and when cucurbituryl bound carbon dioxide leaves the system. Or I can also calculate what's the desorption enthalpies. When I mean desorption enthalpies, when carbon dioxide leaves that surface, what's the enthalpy that is associated with it. So this is a simple example wherein I can predict whether cucurbituryl can bind carbon dioxide, nitrogen. Continuing with that, one more example is, you are all quite aware of CuO, cuprous oxide, and it pentamerizes to give you CuO5O5. That's the structure of CuO5O5. And I have got two different indicators. Sorry, It's not two different indicators. I have got an indicator, and the indicator is there at the organic molecule that you can see. The two benzene rings, the two ring systems that you can see is the organic molecule on the HOMO side. So if this molecule can have any interaction with the indicator that I have got. And before I do that, I just have to check it out. What's the HOMO energy? HOMO, you're all aware that it's the highest occupied molecular orbital, and LUMO is lowest unoccupied molecular orbital. I can find out what's the energy of the indicator that I have considered. HOMO energy and LUMO energy, and the software gives me these two values. And it is minus 4.44 and minus 3.26 electron volts. So the difference is the band gap, which is around 1.18 electron volts. What information I get if I know what's the band gap? Lower the band gap, the standard band gap. So I can have a new molecule with a lower band gap than 1.18, and that indicates that the adsorption becomes much more stronger. If I have got one more molecule at around 7.78 electron volts band gap, then the adsorption is weaker. So before I go with the molecule, I can easily figure it out whether the molecule facilitates strong adsorption or weak adsorption, irrespective of the adsorbent. Now for that particular yellow colored atom, I can also figure it out. I can also calculate what's its Mulliken charge. And in this case, the Mulliken charge is 0.223685 units. Why should I do this Mulliken charge? When I know that Mulliken charge is having a specific number, I can figure it out that whether it is positively charged or negatively charged. And if it is positively charged, whether if it behaves like a cationic center or an anionic center, I can easily identify whether it can have any interaction with another cation or anion, whether repulsion takes place, attraction takes place, all those things I can calculate depending on these Mulliken charges. So in this case, I have got a cationic dye, and it interacts with highest positive Mulliken charge on the cluster. So the one that is there at the top is the indicator, the one where I'm hovering around. Is it one second? Let me have it. Can you see this part? This part. This part is an organic molecule, and the positive Mulliken charge on this atom facilitates the interaction with the cluster, CO5O5 cluster. And on the other hand, if I have got an anionic dye, it interacts highest with negative Mulliken charge on the cluster. So let me assume that this molecule has got a negative ionic Mulliken charge, and then this part interacts with highest negative cluster with anion dye. And I can figure it out what's the interaction energy, and I'll get it in kilocalories per mole. I can do the whole simulation in gas phase, or I can have a particular solvent. And in one of the examples that I carried out, the gas phase energy was minus 17.9 and the solvent phase was around minus 19.4. There is a very little energy difference between these two. Therefore, I can conclude that solvation has got a negligible effect on this. So I can carry out this process in the gas phase, or I can carry out it in the liquid phase. The difference in energy is very, very minimum. So before I perform the experiment, I can easily figure it out whether I can do it in gaseous phase or I can do it in the solvent phase. Again, if it is a solvent, should I consider water as a solvent and the organic solvent as a solvent, or aprotic solvents. I can figure out all those solvents beforehand. This is a slide wherein you can design the molecule the way you wish. And basically this is for, this is not my work, and I had just taken it from one of the published papers from a different author. So these caged molecules are used for drying up the hydrogen gas. Before you procure these molecules, before you have it in your hand, you can predict which of these 11 molecules is best performing zeolite for drying a hydrogen gas. So that's the versatility of in silico studies. And this is the work that was done by one of my students during his MSc project. He started with this molecule, carbon dioxide, and he wanted to convert it into format ion, HCO minus. And he designed 4 catalysts, catalyst A, B, C, D, and he just wanted to design the catalyst. So he has designed the catalyst, he has optimized the structure. Optimization, as I have already said, you just have to give it to the tool. The tool does all those calculations. It stretches the bond, it compresses the bond, it elongates the bond, it changes the bond angle, everything that it does. And at each level, it calculates the energy and gives you the lowest energy possible. And that is what we call it as optimized structure. And when you have got this optimized structure, calculate its energy in one that I have showed you in the last slide, gas phase, liquid phase, and all those things. So carry out that the bond dissociation energy in 3 different solvents. That's what he did it for his MSc project work. He took 3 solvents and those are the energies. Based on this, I can easily say that water is having at a different level, the other 2 solvents are at different level. So if my lab does not have tetrahydrofuran, I can easily substitute it with 1,2-dichloroethane. Or with water, I can expect slightly different property or slightly different reaction condition when compared to the other 2 solvents. And you can also calculate basically this particular image, all of you are quite comfortable with, right? The reaction coordinates. You can track whether the reaction is happening or whether the reaction is going to take place or not before you proceed with the normal synthesis. You know what's the exact energy of the reactants? When you have the product at this level, you know what exactly is the energy of this product. Now, if your chemistry is strong, you can predict that it goes through a transition state like TS1. The TS1 may not be the exact transition state, but we guess that that is a transition state. So we identify one of the transition states. Let me assume that the transition state is somewhere here, right, where I'm referring to. And now I know the energy at this level because this is my observed, this is my transition state. I have drawn the structure. I have calculated what is its energy. The energy is at this level. Now I know that the product is at this level and this is the transition state. Between this transition state and the product, let me think of one more transition state, one more transition structure. That may be somewhere here. Again, I know the transition state 2. I know what is the product. I know what is the reactant structure. Can I guess one more transition state? And the transition state can be somewhere here. That means I cannot have same energy for 2 different molecules. There has to be one more transition state, which is having highest energy. So I can keep working on this. And believe me, each calculation takes less than 15 to 20 minutes. You just have to guess the structure, give it to the system. The system calculates its energy and gives you what's the energy of that particular stereochemistry part of the molecule. So you keep drawing the structures, and in the process, you can find out what's the transition state, which is having maximum energy. Once you have identified the transition state based on the energy, there are tools that are available which can predict whether is that the only transition available or there can be multiple transition states that are available. Those are the things that one can carry it out. And then all you have to do is you have to plot the graph, whatever the energy that you got, starting with the reactants, goes through the transition state and comes back. And in the process, you can calculate all these parameters, entropy, enthalpy, any of these parameters you can calculate. And from there, you can identify whether the proposed reaction works or does not work at the given condition. And again, when you have these catalysts, say, for example, let me assume that catalyst B gives you a good property. Then what you can do is you can modify the functional groups in that. At the para position, I have got NH2 group, or at the para position, if I've got methoxy group or methyl group, I can keep modifying all these functional groups, and I can figure it out whether it fits into the linear equation. I know what is a Hammett substituent constant. I can get it in any other standard textbook. I can correlate with the energy that I get, equilibrium constant, and then plot a graph. Any other substituent which comes here, which I have not at all calculated also, based on this equation, I can find out whether the equilibrium constant is high, low, moderate, or close to this without doing all those things, because I know what is the Hammett substituent for that particular substituent. The moment I know this, and if I have got this graph, I can easily figure it out what's its equilibrium constant. These are the things that one can do if you can think of in silico studies for basically environmental problems. And most of us, when I say informatics or in silico studies, most of the perception is that they are all working on the docking process. You take an enzyme, you take a ligand, and then you dock it, and then go for the publication or any of those things. That is not the end of that particular story. There are lots of things that one can do it. And believe me, you just have to Google it. There are lots and lots of open tools are available, open source tools are available, and you can do all these things. The one that I did is with Schrodinger. Everything is incorporated into one particular cluster, and it gives you a bundle of softwares. Or else, if the money is the criteria, then you can go with all those open softwares. Then you just have to take results from one tool and put it onto the other tool, and you get these results. And again, I started with the video, and I'll end with the video. And the beginning part of the video, probably all of you are quite aware of, but there are 4 levels, and just watch this. Maybe some of your So basically, whatever that I have presented is nothing but a teamwork of myself along with my MSc and PhD students. Thank you. Any questions?
I've enjoyed doing really very nice. Actually, right from the beginning till the end, every slide we enjoyed. Even these small things, every understanding is made. So, on behalf of the participants, we really thank all of them.
Sir, I could not hear you properly. Can you repeat that again? I'm sorry, sir. I could not hear you properly.
Thank you for a nice presentation. Really, you all enjoyed. I hope all the participants will agree with me. Right from the beginning till the end, all the slides have given information for us. The end was very informative, and you have mentioned the keyword is the success of all. It's really a good motivation for all the participants. Regarding the presentation, design, then synthesis, and you have mentioned about the DFT calculations and the kinetics of the work and how this molecule will benefit for the pharma industry. As a researcher on this, I have a question. You have mentioned about the binding energy calculation. The energy gap between HOMO and LUMO is very less. If it is 1.0 something, that is low, it will have a better, strong interaction. Sir, is there any yardstick for this value?
No, it's only the comparative. It's only the comparative values, sir. So you design two molecules, and between the two molecules, you identify which one has got a stronger ability and which one has got a weaker ability.
Let's see, when the energy gap is even less than this, will it be effective or?
I could not get the question, sir. Can you repeat that question?
You have mentioned that what the energy, the band is 1.08. If it is less, it would be the better. It will have a better interaction, stronger binding. Isn't it?
Correct.
Yeah. For any molecule, the value should be within this range, or it may even lesser than this.
Sir, the energy gap values is an indicative value. That's it. It tells you whether the adsorption is a strong or weak between the two molecules.
Yeah.
There is no hard stick that less than 1, it's always a better adsorption. Greater than 2, it's a weak adsorption. There is no hard and fast rule like that. Between the given two molecules, which molecule binds strongly and which molecule binds weakly, that we can predict.
And regarding the substitutive effect, what information actually you have mentioned different substituents, and is there any relationship actually regarding the Hammond equation? You have mentioned that equilibrium constant. Is there any relation between this equilibrium constant and the binding energy?
Equilibrium constant and?
Binding energy, the binding with the molecular binding.
No, sir. Molecular binding energy is different from equilibrium constant.
Is there any correlation between these two values?
No, sir. No, sir. We don't have anything. What I meant to say was you can calculate the binding energy, and also you can calculate what its equilibrium constant. From the equilibrium constant, you can use Hammond's plot and extrapolate that.
Oh, thank you, sir. Thank you. Really enjoyed. Thank you for this presentation. And is there any question from the other participants? You can raise now, please.
Most merciful, most relevant, I feel very proud to present the book of thanks for this technical session. On behalf of the University government, I would like to thank the respected chief guest, Dr. N.D. Anantkumar, Sir, seriously, Department of Chemistry, MIT, Medical Academy of Higher Education, for this interesting, inspiring, and informative talk on essential molecules for pollutant removal, in-situ studies.
Google Tag.
Thank you, sir. Thus, our officer. Take an opportunity to thank the management, organizing team, submitters of today's studies, for all their support and research. Finally, I thank you all.
Thank you, sir. Thanks for those nice words.
Excuse me, ma'am. Hello. Can you hear me, ma'am?
Assalamu alaikum and a very pleasant good evening to anyone gathered here for the valedictory function of 7th International Conference on Innovation in Chemical and Environmental Research. Let us begin this program with Quran. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين الرحمن الرحيم مالك يوم الدين إياك نعبد وإياك نستعين اهدنا الصراط المستقيم صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين آمين. السلام عليكم. It's time to invite the chief dean of chemistry department and what we always seek task to the completion and boys gentlemen is Mr. Dr. M. Sayedali Padusha, Sir, Associate Professor of Chemistry, along with introduction of the chief guest.
Bismillahirrahmanirrahim. In the name of Allah, the most benevolent and most merciful, let me begin. Most respected Additional Vice Principal and Head Department of Chemistry and respected resource person of this valedictory program, delegates, professors of Department of Chemistry and faculty members from other departments, student friends. At the outset, I feel immensely happy to extend a warm and cordial welcome to Mohamed present here for the valedictory program of this International Conference on Chemical and Environmental Research, ICCR 2022. First of all, I am very much happy to welcome our respected Head of Department and Additional Vice Principal, Dr. Mohamed Shinabuli. Sir is a real source of inspiration for all the faculty members of our department and the students. The Department of Chemistry is a icon of this knowledge because all the faculty members of this department are actively involved in research, academic, and administrative responsibilities. It is all because of the support and motivation by our professor and our department. So, on behalf of the organizing committee, we extend a warm welcome to our Head of Department. We welcome you, sir. We are very much happy to welcome our resource person, chief guest of this valedictory program, an illustrious alumnus, blossomed in the garden of Jamal and spreading the fragrance of his knowledge
PhD and MSc from this great citadel of higher education during 1984-89. And then he switched over to the very reputed university of our nation, that is University of Madras. Again, he did his postgraduate program in biochemistry, MPhil and PhD. So, our resource person has 12 master degree program, both in chemistry and biochemistry. After completion of his PhD, he has joined as a lecturer in the Department of Biochemistry of Islamia College, and he served there for some years as a lecturer. Then he moved on to University of Malaysia, that is School of Medical Sciences, University of Science Malaysia University, where he spent more than 2 decades as a lecturer, senior lecturer, associate professor, and then professor. Then Sir was appointed as professor in the Department of Basic Medical Sciences, Institute of Medicine, that is Department of Medicine, International Islamic University, Malaysia. He was honored as a member in different professional organizations like member Malaysian Society of Pharmacology and more than 2 decades of teaching experience. In the field of research, he has vast experience. He has dedicated more than 3 decades of his life for research. So his career, he has operated 40 projects funded by different funding agencies in Malaysia, and he has published 150 research articles in various journals of review. And he has presented abstract for the conferences. This number goes above 120. And he has contributed a chapter for a book and also authored a book, e-book on biochemistry. He has guided several students for MSc, Master of Pathology, and PhD, number around 40. And he has received many academic recognition. He served as a chairperson for MSc and PhD Bioworks examination, and he was the head of distinction of Bioworks, person for scientific sessions in national and international conferences in Malaysia. And he was invited as a speaker for nearly 10 conferences of both international and national level. And he is a proud recipient of many awards and rewards, which includes Distinguished Alumnus Award from our college during the year 2019. And Sir has extended his service to the society in different capacities, like head of Department of Basic Medical Sciences, International University of Malaysia, and he has conducted many community service programs. So the list goes such a caliber, a vital personality. Our alumnus is with us to address all of us on this wonderful event. So on behalf of the organizing committee, management, principal, staff and students of Jamal College, we extend our heartiest welcome to our resource person. We welcome you, sir. It's my great pleasure to welcome Dr. C. Mubarak, Associate Professor of Chemistry, Dr. Jamal Dr. Zakir Hussain, Dr. Sirajuddin, Dr. Riyaz Ahmed, the organizing secretary and convener, Dr. B.S., and other in this conference across the nation, across the globe as well as nation. In the morning inaugural session, convener told that people from Bangladesh and different parts of our nation have joined for this conference. And once again, I thank all the women faculty members. I welcome all the women faculty members and my dear student friends for this validity program. Thank you all.
Thank you, sir. Real leaders are ordinary people with extraordinary determination. And now we have a sophisticated personality, good orator, and a dedicated teacher is our beloved Additional Vice Principal and Head of the Department of Chemistry, Dr. Mohamed, sir. May I request you, sir, to preside over the function. Now I would like to call upon Dr. A. Samshad Begum, Organizing Secretary of ICICER 2022 to deliver the report of the conference. I extend a warm and very pleasant good evening to everyone gathered here. I feel privileged to honor to present the report of the 7th International Conference on Innovations in Chemical and Environmental Research, ICICER 2022, organized by PG and Research Department of Chemistry, Jamal College, Tiruchirappalli. The organizing committee of ICICER 2022 had adopted the theme Innovations in Chemical and Environmental Research for events. The main objective of this conference is to bring together experts from the academic institutions, industries, research organization for sharing their knowledge in the innovations in chemical and environmental sciences. The inauguration of the conference is initiated with the Iraq by Mr. S. Ahmed of Academic Chemistry, Dr. Mohamed, Additional Vice Principal, Head of the Department, welcomed the gathering and presided over the function. The theme of the conference was delivered by Dr. S. K. Pegeswamy, Organizing Secretary and Convener, ICICER 2022. The survey was the conference was released by Dr. Mohamed, Additional Vice Principal and Head of the Department of Chemistry, Jamal College, and followed by the first copy of the survey was received by Dr. M. Sini Goret and Dr. A. Mohamed, Associate Professor, Department of Chemistry, Jamal College. Dr. A. Jafar Ahmed, Associate Professor of Chemistry, introduces the resource person of the technical session 1. The inaugural address and the keynote lecture was delivered by Dr. M. Mohamed Shakawat Hussain, Principal, College of Science, Engineering and Management, London, United Kingdom, on the topic template-less growth method for capacitive nickel, cobalt, and nickel-cobalt nanocomposites, nanowraps, nanowires, and nanocrystalline planes without any pre-treatment or directly on aluminium, titanium alloy by ultra-high-speed electrodepacitors. The ICICER 2022 is a forum which brings together the researchers, scientists, and industry professionals to discuss innovative ideas and diverse topics on next generation of chemical and environmental science and technology. ICICER 2022 was joined by delegates from different countries like UK, UAE, Malaysia, and Bangladesh, and also from the different states of our nation. Technical session was started with an invited talk by Dr. A. Srinivasan, Senior Scientist, Center for Nanomaterials, International Advanced Research Center for Powder Metrology and New Materials, Hyderabad, Telangana. He delivered a lecture on the topic Design, Development and Demonstration of Advanced Nanostructured Materials for Energy Storage Applications. Technical session 2 began with an invited lecture by Dr. M.D. Anil Kumar, Associate Professor, Department of Chemistry, MIT, Manipal Academy of Higher Education, Manipal, on the topic Design of Molecules for Pollutants Removal in Silico Studies. The oral presentation was held parallelly at the technical session 3. The conference featured versatile lectures from the experts across the nation and worldwide. More than 400 participants Interest researchers, industrialists, and students have benefited from this conference ITIT year 2022. Nearly 130 research articles have been presented already in the 5 parallel sessions. Among them, we have received abstracts from the various countries, UAE, UK, Bangladesh, Malaysia, and also from the various states of our country like Kashmir, Maharashtra, Hyderabad, Manipur, Kolkata, West Bengal, Punjab, Haryana, and Uttar Pradesh. A keynote lecture on natural products, a neural degeneration, and narrative address of ITIT year 2022 will be delivered by Professor Dr. K.S. Sirajuddin, Head Department of Basic Medical Sciences, Kuala of Medicine International Islamic University, Bandar Bahang, Malaysia. The organizing team of ITIT year 2022 solicit your presence and validation and fullest cooperation for the smooth conduct of the conference. Thank you very much for the wonderful opportunity. Thank you, ma'am. Now I would like to invite Professor Dr. K.S. Sirajuddin, sir, to deliver validity address. Please, sir.
Assalamu alaikum wa rahmatullahi wa barakatuhu, and very good afternoon. Dear professors, researchers, and students. Thank you for Professor Syed Ali Badshah for your kind introduction. I am honored to join the validity session of the 7th International Conference on the Innovation on Chemistry and the Environmental Research 2022, organized by the PG Department of Chemistry, Jamal College. I am very proud to be an alumnus of Jamal College and from the Chemistry Department in particular. I would like to thank all my professors of Jamal College who taught me the subjects. As we know, many alumni of Jamal College are now in a very high standard, the distinguished person in the society. I pray the Almighty for our Jamal College to continuously excel in the fields of education and innovative research, and thereby provide an excellent service to the nation. So I would like to thank our Jamal College top management, the president, the secretary and correspondent, the treasurer, principal, vice principal, and then the additional vice principal, head of the Department of Chemistry, my teacher and mentor, Prof. Sihabuddin sir, the organizing secretary, Dr. Periyasamy, and all the organizing committee members for inviting me to this conference. As we know, the chemistry is often regarded as the central discipline, which links together with physics, mathematics, biology, medicine, earth, environmental sciences, and many more to complement each other and showcase the science, what we see as a whole. There is ever expanding opportunity of research in different fields of the chemistry. Needless to say that the environmental chemistry is an most important emerging area that can help us to understand, monitor, protect, and improve the environment that we are living in. So the another potential research area of chemistry is the natural product chemistry. The natural products are the products from various natural resources, such as the plants, marine, microorganism, and animals. Either it can be an entire organism or a part of the organism like leaves from the plant or a particular section of the animal organ, an extract of an organism or part of the organism and exudate or a pure compound. Like chemistry, you know, the alkaloids, flavonoids, steroids, and terpenoids. which are isolated from the plants, marine, animals, or microorganisms. So as an alternative medicine, the natural products are being used since ancient time for the treatment of various ailments. And the natural products are the important source of new lead structure for the development of many drugs due to their various biological activities, like antioxidant, anti-inflammatory, and apoptotic properties. For obvious reason, there is a global trend toward the use of the natural product, which not only promote the human health and prevent the diseases, at the same time, it minimizes the detrimental side effects of the various synthetic drugs. So as we know, currently the global warming and water pollution is a big issue. Therefore, there is a need for the green chemistry to design, develop, and implement the chemical products and processes that reduce or eliminate the use and generation of the hazardous material. In today's conference, you are attending many scientific sessions and have listened to an excellent presentation from our distinguished keynote speaker, as well as from invited speakers. Prof. Dr. Hussain presented about the high-speed electro forming to make a nano-structured material in one-step method. Very nicely, Dr. Srinivasan presented about the design, development, and demonstration of the advanced nano-structured material for a renewable energy storage application, which is the very, very important field now. The energy, the field is the renewable energy is the main hot topic. And Prof. Anil Kumar presented an in silico studies about the designer molecule for pollutant removals. So I am sure that the conference can serve as an excellent platform for those involved in the chemical and environmental research to share their knowledge, innovation, and expertise from the learned speakers of various disciplines. I hope that the participants will take this opportunity to exchange and share knowledge to update their understanding in their field of research. I request the young researchers and then the students to plan to do a good basic and fundamental applied responsible research, which are much needed to benefit our society. Another point I want to insist is the collaborative research. As we know, in this globalized world, networking is very, very essential for everyone to learn from each other for further development as well as for the well-being of the society. So there is no alternative to collaborative research and networking for the advancement of the multidisciplinary research. To extend, because already the conference is, the time is already extended. So I would like to conclude the remarks. And once again, I would like to extend my felicitation to the organizing committee for conducting such a brilliant successive conferences over the years. Finally, I would like to thank everyone and my best wishes to all the participants. Thank you so much.
Gratitude, praise, everything I will do. To your appropriate end, this formal event, I invite our to closing developments.
The name of Almighty, the most beneficent and merciful, I express my sincere thanks to the God Almighty for the successful conduct of this 7th conference. I express my sincere gratitude to the management committee, Honorable Secretary and Correspondent, directors, for providing all sort of facilities to conduct this program. I express my sincere thanks to our beloved principal, vice principal, additional vice principal, and our beloved department for their motivation and guidance for the conduct of this international conference. I wish to place on record my sincere thanks to the research persons of today, Dr. Mohamed, Principal, College of Science, Engineering and Management, London, Dr. K.S. Department of Basic Medical Science, International Islamic University, Malaysia, Dr. Senior Scientist, Center for Power Metallurgy and New Materials, Hyderabad, and Dr. A.V. Anil Kumar, Associate Professor, Academy of Higher Education, for their illuminating lecture, which enlightened the budding chemists and students of our institute and various institutes. I express my sincere gratitude for the participants from United Kingdom, United Arab Emirates, Bangladesh, and various states of our nation, from Uttar Pradesh, Madhya Pradesh, Karnataka, Punjab, and Haryana, for their patience and participation in this 7th International Conference. I express my sincere thanks to Dr. Isaiah, Associate Professor, Bishop Ibn College, Dr. V. Priya of Holy Cross College for chairing the technical session. I place on record my sincere thanks to Professor Kannan, the combo technical support provided, and I express my sincere thanks to the moderators of this conference and the Department of Physics for providing the hall for the conference, and I express sincere thanks to my students, your patient listening and your enthusiastic participation from the morning, and I thank everyone who contributed for the conduct of this conference. Thank you. Thank you very much.
Everyone stand up for national.
For national.